the point of this talk is to go through a data science workflow and to start at the very beginning. And well, we'll see how far we get, actually. I want to take a quick read of the room before we jump in. How many of you are fairly comfortable in Python? This will be mostly in Python. OK, that's a good sign. And how many of you would say you're somewhat less comfortable in Python? OK, a lot of you. So hopefully, for some of you who are newer to Python, you were able to make Skipper's talk this morning, because we'll be making some use of it. We won't go too much into the language itself, but I'll slow down in a couple places to point out some of the features of the language. But most of the time, we're going to be talking about data science and how we actually use some of the core machinery of mostly Python libraries to do a data science workflow. Turn on my computer here. So there's a few parts to this talk, and I'm going to walk you through all the stuff that hopefully you will have downloaded within the next few minutes to help you follow along. If you are having any trouble with that stuff, Skipper will be paying attention and walking around the room a little bit, so feel free to flag him down if any of this looks a little bit scary to you. But I want to just start with some of the prereqs here. So there's a GitHub repo that is the best place to get started with this stuff. The internet seems to be really slow. But it's in my it's under my Git account, which is CM Malone, and then it's called ODSC 2017 Data Science 101. And that's what has all of the notebooks that we'll be working from, and also there's a link to the slides in there as well. So while it looks like everybody's trying to download stuff right now, so my internet isn't working. But let me walk you through what we'll be doing today and what we're going to try to accomplish. So first, let me introduce myself a little bit more. So like they said, my name is Katie Malone. I work at Civis Analytics, which is a data science software and services company out in Chicago. And what I do as part of the data science research and development role is think a lot about what are the data science methodologies that we use to solve business problems on behalf of our clients, and what are some of the ways that we can put those methodologies into software. And so my talk is very much informed by that. In the latter half of our talk, we'll see sort of how far we get. Since this looks like a crowd that is still fairly like getting used to Python and maybe getting used to scikit-learn as well, we'll kind of see how far we get. But one of the things that's been really important to me as I've been working in this role is not just thinking about how do we solve machine learning problems for data science, but how do we do it in a maintainable way? How do we write not just scripted workflows that solve a data science problem once, but what are some of the software engineering best practices so that we can break up those workflows and turn them into something that's more reusable, that's more user-friendly, that's more maintainable, that's less likely to break. Before this, I was a physicist and spent some time out here in the Bay Area. I also taught a machine learning class for Udacity, so some of you may have stumbled across that. And it actually has a lot more detail about the scikit-learn library that we'll be going through today. So if you find yourself really interested in some of this machine learning stuff and interested in learning more, that is a resource that I can personally recommend. And in my spare time, I also have a podcast about data science and machine learning and stuff like that. It's called Linear Digressions. If that's your jam, check it out. So here's my tentative agenda for this workshop, but we'll kind of see how it goes. I want to make sure that you all are getting as much out of this as you can, so we might slow down in some places and speed up in some other places. But what I'm going to do in the first half or so of the talk is go through an end-to-end data science workflow. So starting from a data set and a problem that is defined on that data set, how do we go through the big pieces of putting together a machine learning workflow so that we can solve the problem? And thinking through some of the reasons for what those pieces are that we want to use and why we want to use them. Obviously, we're just going to sample a little bit of the machine learning space. You're never going to learn everything in 4 hours. But hopefully, you get a sense for what some of the big moving pieces are. Then in the second half of the talk, we'll take probably a 15-minute break about halfway through so you can stretch your legs. And then we'll make it as maintainable as we can by switching from the Jupyter notebooks over to Python scripts. Jupyter notebooks are great for exploration, for communicating your results to other people. But if you want to make a family heirloom type piece of software, Jupyter Notebook is not the first choice for that. It's usually Python scripts. So I'm going to walk through how to take the basic workflow that we've outlined in the first half of the talk and start splitting it up into pieces and putting those pieces into a Python script. And again, sort of depending on how time breaks out, by the end of that, we might be doing things like putting a command line interface on our program, writing a simple unit test. We're moving towards something that really starts to look like data science software. And that transition is something that I think is really important and somewhat harder to learn sometimes than the core machine learning stuff. There's a lot of places, I think, where you can get some good experience that overlaps with the first half of this talk. We'll still go through it in some detail because I think it's really important. But the second half of the talk for me, it's a little bit more advanced, and it's going to stretch different muscles than what you stretch if you're doing, say, Kaggle competitions, because it's just a different way of thinking about data science software. Because again, it's more about making it robust and maintainable and not necessarily about just getting an answer or tuning hyperparameters. And then at the very end, hopefully we'll get to a point where we have several different versions of the model that we've built, and we can start to make some really interesting comparisons of those models against each other and to say some meaningful things about what maybe makes the models different. So I want to talk just a little bit to frame, in particular, the second half of this talk, but we'll come back to this. Some of the things that I think make real-life data science different from what I'm calling competition data science here, but it's also like data science that maybe you've done as homework for a class or that kind of thing. Very often in let's say, homework data science, the problem that we want to solve in machine learning is fairly clear, and it's very easy to articulate exactly what it is, because there's a data set, and in that data set there is a column, and that column is called labels or predictions or some values that you want to predict. And so the thing that you're trying to do with machine learning is use all of the information that's in the other columns of that data set to recognize patterns that help you predict that thing that you're interested in. But very often in the real world, we don't actually have something that's that well defined. We have to define for ourselves what it is that we want to accomplish and where might the data be that would allow us to measure that. What's some kind of proxy that would allow us to measure something like customer lifetime value or customer churn? Like, what does that even mean? So it can get a lot trickier sometimes just at the problem definition step in real life. We'll be using a pretty clean data set with a pretty well-defined column here, but I wanted to give a nod to it as a place where things start to get a lot stickier once you get outside of kind of like a more controlled environment. Where the data comes from and what it looks like is also another place where things can get really tricky. This could easily be a workshop entirely in its own right, but anyone who's worked with quote-unquote real data knows that sometimes it's really messy. The data that we'll be working with today is pretty clean, which makes it really nice for this kind of environment where we want to move fairly quickly, but it's not uncommon to spend weeks sometimes just understanding and cleaning your data set. Once you have a data set that's cleaned and you know what the question is that you want to answer, you have to define that in a mathematical way. What is the thing that I'm optimizing for that allows me to, once I've figured it out, will actually solve the problem that I care about? And so for something like a competition, this might be something like the out-of-sample accuracy. We'll talk a little bit about what that means. But it's just saying, like, there's a fairly simple metric. How many questions or how many predictions did I get right? And how many did I get wrong? And just the ratio between those is the accuracy. It's fairly well defined. And I will sometimes go to maybe very far lengths to get extra little 1% boosts in that accuracy. What I think from where I sit working on this stuff professionally, smoothness and clarity of the delivery is much more important. So I will any day give up a couple of percentage points on the accuracy of my model if it's something that's maintainable, if it's not something that's going to be breaking all the time. And that's something that I think is easy to lose sight of when you're working sometimes in a more controlled environment. And then the last thing, which is related, we'll talk a little bit about model selection and hyperparameter tuning. So this is how do you actually pick the best model of the many options that you might have on the table. But the thing that I think about more is like, how do we make stuff not break? So again, these are things that we'll nod toward much more in the back half of the talk that I think are harder to get sometimes from like classroom experiences or from Kaggle. And so that's why I think they're pretty interesting. So the problem that we're going to be working on today is from a drivendata.org competition. Driven Data is really similar to Kaggle, but with kind of a social good focus, which I think is really cool. And they have this challenge, and what they have there is a data set that has a bunch of attributes of water wells in Africa. And what you're trying to predict is whether the water wells are functional, they're functional but they need repairs, or they're non-functional, based on the other attributes of the wells that you see recorded in the data set. And so we'll walk through this in sort of a very straightforward way in the first half, but the twist that I want you to be thinking about as we're going is imagine that we don't have a scenario in which we have all of the data sort of presented to us at once at the beginning. Imagine that you're the data scientist who's sitting here in San Francisco, and maybe there's an analyst who's on the ground in Africa, and they're working with a team. And that analyst has to be running your code, and they have to be using your model to make predictions for that team to go out and make inspections the next day. And that team, likewise, is going out and doing those inspections. They're collecting more data. They're sending it to the analyst, who's then sending it back to you. So you have something in which there's incremental updates that are being made to your model. There's new data sets that you have to incorporate very smoothly, and those can break if you're not thoughtful about how to incorporate new data. And moreover, the model itself has to be run by somebody who isn't super technical. So they don't really want to be debugging your code. They want to be interacting with it as minimally as possible. So we have to be a little bit protective about what are some of the common failure modes, and what are some of the ways that we can help make it more user-friendly. So again, in the beginning half of this talk, we'll just walk through how are we even going to solve the problem in the first place. But then as we're doing that, keep an eye or a bit of a mind toward what would be the modifications on this procedure that we would have to make in order to make this something that we could use again and again and again, or we could hand off to someone to use again and again and again. So the data sets for this competition, there's the Git repo if anyone still was looking for that. The data sets for this competition you can download directly from drivendata.org, and hopefully most of you have been able to do that already. If you haven't, we have flash drives that have copies of the data sets on them. There's slightly different versions of the data sets that we use in the first part and the second part. So just a quick show of hands before I go too much further. I want to make sure that we get those handed out for everyone who needs them. If you do not have the data sets and you would like a copy on the flash drive, can you just raise your hand real quick? And then leave it up until Skipper comes around and gets you a flash drive. OK. So while he's doing that, I'm going to keep going, though. Hopefully, a lot of you, I think, were here a few minutes before this started and were able to start getting your environment set up if you didn't have it already set up. So we're going to be making pretty heavy use of Jupyter notebooks in the first part of this talk, and be running a lot of scikit-learn, using pandas, NumPy and SciPy. And then this was a late addition, so some of you might not have it, but we're going to try to get to PyTest at the very end of the talk. If you don't have PyTest, I think you can still get plenty out of this talk. Don't sweat that one too much. And then the last thing I'll mention is I'm going to be working from these slides in large part, and then kind of hopping back and forth between these slides and code. All the code that I will be showing you is in the Git repository, and that includes the Jupyter notebooks as well. So if you want the slides, there's a link to them on the README of the Git repo. There's just a Dropbox link. So if that would be helpful to you to kind of have the slides sitting on your laptop alongside your terminal, I know that helps me sometimes. Feel free to make use of them. You can get them on the Git README. Any questions about any of that stuff before we start digging in? OK, cool. So let me switch over to a Jupyter notebook now, because I think it's a better way of illustrating this. So there are two different versions of the Jupyter notebook. And I think that with this crew, because I think a lot of you are keen to get your hands on the keyboard, what I'm going to encourage you to do is use the notebook called scripted model to fill in .ipynb. And then there's also one that's just called scripted model. Can you maximize it? Oh, yeah, sorry. This just called scripted model ipynb. And the difference between them, they're exactly the same, but to fill in is going to have a few boxes of code. Let me show you an example. So to fill in is mostly filled in with working code, but there are a few of them that are not actually filled in. So the way we're going to do the first part of this talk is I'll walk you through sort of the concepts and show you what it's supposed to look like. And then I will take my foot off the gas a little bit and allow you, maybe 10 minutes here, 15 minutes there to fill it in and to get the code actually working for yourself. But I mentioned it to you so that if you get stuck on any of it, there is a fail-safe, which is you have all the answers in that other notebook. So don't panic if you're finding it a little bit challenging. OK, so Jupyter Notebooks, if you haven't worked with them before, just a quick orientation. I think they're really great for exploratory data analysis and for communicating. And so there's the markdown cells that give you this nice formatted text, and you can make plots in them and all this sort of stuff. But then they also have these working code cells as well. And so the way you execute the code is with Shift-Enter. So I just hit Shift-Enter, and now it's actually loading up these data sets for me. I renamed the data sets well data and well labels because I thought that was a lot easier to read than the download file names. They were just these long, like alphanumeric strings. And shortcut to insert code.
Yeah. Go to code window. I noticed last session you were just popping those in left and right, and I didn't know he was doing.
What do you do? Hit enter?
Yeah.
OK.
Yeah.
Oh, you just go like.
Yeah.
I think mine's still running.
I don't think you're connected here currently. Might need to restart.
Oh, OK. Thank you. So let's try this again. Hopefully this is working. There we go. OK. So this is an example of it working. So I've ended it with just a print statement, and it's just printing the first 20 rows in my well labels. So this is we're starting to look at the data now. The data is in two different files. So well features has, I think, something like 40 columns or so, and these are all attributes of the wells. And then the labels live in a different data set. It's called well labels. And so when you actually look at the top of this data set, you see that there's basically three different classes that, well, you only see two of them here. Oh, yeah, we see all three of them. So there's three different classes that we're going to be classifying. Like I said before, the wells can be functional. They can be functional but needing repair, or they can be non-functional. And so the main thing that we're going to try to do is for wells that we don't know what the answer is, or we pretend that we don't know what the answer is, we're going to try to make predictions for which of those three classes they belong to based on the features of the well themselves. So a little bit of this now, just to take a quick look at the features data. The features data is kind of interesting. There are a few things I want to point out to you here. One is that a lot of the features here are strings, as you can see. The water point type, for example, communal standpipe is a string. And this is going to be a little bit of a challenge for us because machine learning algorithms use stuff like calculus and linear algebra. And you can't do calculus on strings. You can only do calculus on numbers. So we're going to have to do some feature transformations in order to get the data into a format that the machine learning algorithms are actually going to find acceptable. So with that preamble, let me just stay here. So the first example I wanted to go through was actually just doing the mapping of the labels onto integers. This one I've just supplied the answer for you here so that we can keep moving and not get too stuck on this. But there's a lot of different ways that you can transform strings into integers, right? And this is just one of them, but you might have another way that you find satisfactory. But the whole idea here is that we want to come up with some kind of mapping of the labels onto integers so that, again, we can send this into our machine learning algorithms. So the mapping that I've picked out here is we're going to say that functional, we're going to encode as a 2. Functional needs repair, we're going to encode as a 1. And non-functional, we're going to encode as a 0. And so here's one of the ways that you can do that is you can make what's called a map that will return to you the integer value depending on which string you send into it. And then if you apply that map to your data frame, this is like a pandas manipulation, then this will actually transform the labels that you have in your data set, in your data frame. So this is me actually running this code and then printing out the top 5 entries in my labels data set. So the things that were functional now are all encoded as 2s, and then it looks like there's a non-functional that's encoded as 0, and then we don't happen to have any functional needs repair in this snapshot of the data. But if we were to, as it happens, there's just not that many of them. So we'll come back to this later in the second half of the talk. But for right now, this is just a simple example of how we can do one of those transformations. Are there any questions on this stuff so far? OK, cool. So we have to do something similar with the features. So the features, as you saw, are largely strings. And now, again, there's a lot of different ways that you can transform features to strings, but it's going to be a little bit more challenging in the case of the features. Because number one, there's a lot of features. There's roughly 40 features to this data set. And you don't necessarily, not all of them you need to transform. 40 is just kind of a lot to keep track of. If there's just one column, things are pretty orderly. But instead, what we have to do is write some kind of function that's going to transform all the feature, like each individual feature that we want to transform, and then think about which features we want to apply that to. So let me go back up to the data frame and talk a little bit more about what I mean. So these are all examples of features that we'll need to transform because they're strings. So stuff like quantity group, source, source type, source class. Those are all going to have to turn into integers somehow. But something like num private, I don't exactly know what num private means, but it looks like it's an integer, and so I want to leave that alone. Or latitude and longitude, so this is where the well physically is. Maybe there's some kind of pattern in there that helps us understand if it's going to be functional or not. So those are examples of columns that I don't want to encode as integers because they're already in some numerical format that's going to be pretty good for machine learning. So I have to be a little bit more thoughtful about what the columns are that I wanted to transform. So here I've actually just written a list of the things that I personally think are good candidates. And the way that I got these was just by looking through the data and for each column saying, does this look like it has a bunch of categorical strings that we want to transform? And then I wrote a function that I've called transform feature here. And what you do is you send in the data frame that has your features in it and the name of the column. So it's just going to apply to that column as you're doing the transformations. And then that function I've written the body to up here. I don't want to go into the details of this code too much. We're going to come back to this again and write it in using some scikit-learn stuff. But the general idea is that after you've done this transformation, your data set, instead of having a bunch of strings in it, should have a bunch of numbers in it instead. So let me just show you what that looks like. So now all of these strings that had been strings before are now integers. I promise I'll get to the hands on the keyboard stuff really soon. So this is kind of all the work that we need to do in terms of feature preprocessing to get a kickstart and to start doing machine learning. So can I get a quick show of hands? How many of you have done some kind of machine learning before? So a healthy number. And then how many of you, this is one of the first times you've sat down and worked with machine learning? OK, so about half and half. So we'll spend some time talking about the algorithms that we're going to go through. These are just a few of what's, arguably there are hundreds of types of machine learning algorithms. But these are some of the big ones. So let me just show you how to get some of these up and running. I use scikit-learn for this. And scikit-learn is like the best library in Python for doing machine learning. And the thing that's really nice about scikit-learn is it has a very regular API, and it makes it really easy to swap in and out different types of algorithms. So as long as you are thoughtful about making sure that you're using an algorithm that's applicable to the type of problem that you're doing, scikit-learn is going to allow you to swap in algorithms really quickly. So let me show you what this looks like, and then I'm going to have you code up the first algorithm yourself using scikit-learn. show you what this code looks like. So first, let me just take a brief digression into the types of algorithms that you might use, and then I'll tell you the actual algorithm that we'll use a few different kinds here. But before I do that, I want to just talk a little bit about how you can, what's the general taxonomy of machine learning algorithms. So there's two kinds of machine learning, very roughly speaking. There's supervised and unsupervised learning. We are doing supervised learning because we have labeled examples that we can train our data on. So we have all of these well labels where we know for a given case it was functional or non-functional or functional needs repair. And we can use those labels to help guide the machine learning algorithm to understand what patterns in the data allow us to predict it. So what these algorithms are going to be doing under the hood is they all have different assumptions and different structure underneath the hood. But in general, what they're trying to do is they're trying to, they have a set of rules for how they're going to try to find patterns in the data. And then they're going to play around with how they interpret those rules in such a way that they're going to try to get the most accurate predictions that they can on the training data that we send to them. So that's an example of supervised learning. Most machine learning that you come across, especially when you're starting out, is supervised. And in particular, we're doing classification. So, excuse me. There's two different kinds of supervised learning, again, very roughly speaking. Classification is where you're trying to apply discrete labels to different classes. So chocolate, strawberry, vanilla, dogs, cats, fishes, whatever. And in particular, with classification, there isn't usually the expectation that there's any order to the classes. And this is a little bit untrue in our case. I would say that maybe there's an order to functional needs repair, and non-functional, that there's a natural ordering there. And if there's something that's truly ordered, like if you're trying to predict something like age or income or temperature, something that's continuous, then you're in more of the regression regime. So regression is just a different type of algorithm that has a continued or ordered output. And we're a little bit in between these two regimes. We're in what I would call probably ordinal modeling, where we have ordered categories. So we have some discretion for which type of algorithm we want to use. We'll use classification because it's really easy. But a reasonable solution here would be to use regression as well. And then we would just have to bucket the predictions that we get. And we would say something like, OK, all the predictions are going to be between 0 and 1. And everything that's from like 0 to 0.3, we'll say, is non-functional. If it's 0.3 to 0.7, it's functional needs repair. And if it's 0.7 and above, it's non-functional maybe. So the first algorithm that we're going to use is called logistic regression. I'm going to go back and explain this in just a few slides, but I've been talking for far too long and you've been not typing quite enough, so I want to stop now and allow you to get your hands on the keyboard. So in that cell in your Jupyter notebooks, this is going to be the first time that you code up a scikit-learn classifier. So go ahead and get started on that now. This is literally, literally just the code that you need to type. So you can get started on that now. I'll walk through it a little bit in maybe about 5 minutes or so, 3 to 5 minutes. And I'll walk around a little bit if anybody is getting stuck on this. But I want to make sure that you all don't get a little bit too sleepy here. So I'm going to stop talking for a few minutes while you get this coded up, and then we'll come back. OK, folks. So for those of you who got an error that said features is not defined, that is my fault, because I put features here instead of, I think, features df. Features underscore df. Yeah, so it's the same thing. So let me, it's called features df, right? OK, so this is code that should actually work. I apologize for that. But I think a lot of you managed to get it going. Quick show of hands, how many of you were able to, or like now that you're trying it with not typo-riddled code, how many of you were able to get it working?
It's not working for me.
OK, even with the underscore?
It says that the variables are split can be two being.
Variables x and y, sorry.
The variables are x and y.
Oh, okay. All right. Okay. So here, yeah, let me show you what I did. Again, apologies for not having quite the right translation between these two things. So let me use the version of the notebook that has the answers. Yeah, so this was my fault. Sometimes you have to take the data out of the data frame before you can send it into the machine learning algorithm. That was my fault. But let me show you just real quick. This is the version of the notebook that has the solutions in it. So when you have, after you've pulled the data out of the data frames, I neglected to put this in here, but now they're X and Y after I pulled the data out of the data frames, and now this should work. So a few things about this. So one is that we didn't talk about what cross-val score is. We'll come back to this in a little bit, but in general, one of the things that you have to be careful of when you're building a machine learning algorithm, of course, is it needs to be optimizing towards some kind of score. It has to have a thing that it's trying to achieve. So in this case, it's probably something like accuracy, or which is a metric for how good the algorithm is. And so in general, you want to be working with, you want to, as quickly as possible, start to get metrics out of your models. And so that's a little bit of the point of this first part of the talk. We went through it really quickly, and I know we didn't explain a lot of things. But the thing that I find really helpful when I'm building a machine learning pipeline or machine learning workflow is get to a point where you have the model working as quickly as possible, even if it's not working particularly well, and even if you don't think it's very well optimized. And then you can go back and make incremental improvements to it in a way that will hopefully improve the model. And the way that you know if it's improving the model is if you see these, something like the cross-val score go up. So these numbers right now are at about 0.65, 0.66. We'll go back and explain a little bit more about what are some of the different metrics that we might be using. But the thing that you should be looking at is that, they go from 0 to 1, and higher is better. So this is not bad, but we can do a lot better. And sometimes doing better is just as simple as changing around the algorithm. So in just a little bit, I'm going to talk through all these algorithms and what they're actually doing. But one of the things that's really nice about scikit-learn, as I said before, is it has a really clean API. And so you can swap things in really fast. And so I wanted to just sprint ahead and do that first and try swapping out a few different models for each other just so you can see how easy that is. So there are a couple different models that we're going to use here, which is a decision tree classifier and a random forest classifier. And these are just a totally different structure of models. So again, I'll talk about what makes these different from logistic regression in just a couple of minutes. But I want to give you another 5 minutes or so now to get this actually up and running. And I'm going to leave up the working notebook so that I don't make any more PowerPoint mistakes. And you can see if what you get in your notebook is looking comparable to this. And again, I'll be walking around for those of you who are still having some lingering problems with the first part. Okay, so I think we'll keep going. I know a few of you still have, I saw a few lingering hands up. So I'm going to keep things moving, power on ahead, but we'll continue to make the rounds as we keep coding on this. So some of you were a little bit concerned by, there's a warning that you get with, I think, cross-val score. So when you're executing some of that code, there's like this pink warning box that pops up. That's not necessarily a problem. It just means that this code isn't going to work in like 4 years when they finally move that function out of scikit-learn. But for right now, it's not necessarily a problem. So just quick show of hands to make sure how we're tracking. How many of you were able to get this part of the code running as well? Oh, OK, great. So most of you. And then for those of you who are still having a little bit of trouble, again, the solutions are there. And I'll continue to make the rounds as we do stuff. But there are probably a few things that you noticed right off the bat. So first is we went from 1 algorithm to 3 algorithms in just a few lines of code. And they were basically the same lines of code. We just copied and swapped out different types of classifiers that we were calling in scikit-learn. So this is what I meant when I said scikit-learn is really easy to work with. It's just sometimes as simple as changing a couple lines of code, and you can get an entirely new algorithm working in there. And different algorithms are strong with different types of data. This is what we'll talk about in just a second. But in general, logistic regression, that was the first model that we ran that had those, remember those 0.66, 0.65. Those are respectable scores. I've made many models that are much worse than that. But the decision trees and the random forests are doing a lot better. These are 0.74 or 0.79. So these are actually pretty solid models, and we didn't really have to do that much to get to them. There's still some ways that we can probably improve upon that, and that's the next part of the talk. But the main thing that I wanted you to take away from this is that the only thing that was really hard about this, besides making sure that like your directory is pointing at the right data files and stuff, was transforming those strings into integers. And even that isn't really that hard. It's sometimes a little bit of a hassle. But once you have a data set that's a nice square set of data that you can send into one of these algorithms, they'll take you pretty far. And it's not too much work, which is really nice. So let me talk a little bit now about the algorithms themselves, because let me skip ahead a little bit here. Because that's something that we went through a little bit quickly. So I'm going to actually talk about what are these algorithms doing under the hood, and how can we think about whether they're strong or not. So the first thing that we tried is what's called a logistic regression. I think this is a little bit of a bad name for this algorithm because regression makes it sound like a regression algorithm, but it's actually really a classification algorithm. And this is really similar to linear regression, if that's something that you're more familiar with. But it generally belongs to a class of what's called linear models. And the way that linear models work is they have all of these columns of the data, and it's going to try to find what we call coefficients or betas. They're basically multiplication factors for each of those columns, such that when we multiply each column by its coefficient and then we add them all together, that gives us something that is, in the case of logistic regression, something that's like a 0 or a 1. Now it'll actually be something that's more continuous. It's like smoothly continuous between 0 and 1. So what this actually looks like, functionally speaking, is there's this logistic function. That's what that f of x is. And each one of the features that we have in our data set, so like the funder source and the sub-village and whatever else, gets multiplied by one of these coefficients. The machine learning algorithm has to figure out what value that they have, but that's what it's thinking about when it's actually training. You multiply them by each of the columns. You sum them all together for a given row that you're trying to predict, and then you stick that expression into this function. And that's going to give you back some number that's between 0 and 1, exclusive. It won't get all the way to 0 or all the way to 1. But that number you can kind of interpret loosely as a probability. So it's a fairly simple model in terms of it's just multiplications and additions that you're doing to try to understand what the patterns are and to represent the patterns in the algorithm. But it'll give you something that's kind of similar to a probability, and then usually in logistic regression what we do is we say if that probability is greater than 0.5, then we say it's a 1, and if that probability is less than 0.5, it's a 0. We have some discretion to play around with what that threshold should be, but by default it's 0.5. And in particular, logistic regression, it comes to us actually originally from statistics. And so statisticians have been thinking about linear models for 300 years. And there's all kinds of modifications that you can make on logistic regression to help speed up the fitting, to help understand, to help like control the dimensionality, how many different features it's going to be looking at when it tries to fit. And so all of the things that maybe you would do to modify this algorithm, by and large, are going to be different parameters that you can set in scikit-learn. So the scikit-learn documentation is actually, I think, some of the best documentation of an open source library out there, period. It's really, really good. And very often when I want to learn about something new in machine learning or I want to remember how something works, I don't memorize it. I just go back to the scikit-learn docs. And so they're really, it's a really excellent resource for helping you understand what are all the different things that you can tune in these models, and then how do they affect the models. So we'll look at some examples of this in a little bit. But regression has, or logistic regression has some limitations. In particular, it's making a pretty strong assumption that the only thing that we can do is do this multiplication and addition. And anything that falls outside of that realm is not going to be well represented by this model. This model is kind of strict about the patterns that it can find, and there's a lot of stuff that it can't find. So what are some of the things that it can't find? Well, in particular, it's making an assumption that there's linear relationships between each of the features and the probability that we're trying to predict for these wells. So here's a few examples of what this might look like. So let's say that we're trying to understand how the functionality of the well is related to its age. So maybe there's a few different hypotheses I might have. The first hypothesis is that when wells start out, there's a little bit of a break-in period, and then the functionality in general tends to get better as they go along. Maybe there's some reason that you could think of why, like all the stuff that could have broken has already broken, and so they're more reliable after a while. And there's some linear relationship, like the probability that it's going to break for each year is an incremental 10% or something like that. And then likewise, maybe there's a different relationship that we could find. Like they start out pretty high probability of functionality, and then there's this linear decline that you see as the age continues to well, or as the well continues to age. These are things that a logistic regression is going to pick up on really nicely. It can handle those. But what if it's something that's not linear? What if there's something like a really dramatic break-in period where this is like, imagine, this is what I always think of when I'm chewing gum, right? The first 30 seconds that you chew gum, it's really, really good, and then it just like falls off a cliff. At least that's how it feels to me. Maybe wells are the same way, where they're really great right away, and then there's this steep drop off, and maybe there's like a long tail where they're functional, but there's a kink in that. It's not a linear relationship. Or whatever other random nonlinear relationship you can think of, there's semi-infinite numbers of nonlinearities that you might have in your data. Logistic regression is not going to get this very well. There's ways that you can kind of bend it over backwards to like force it to do this stuff if you really want it to, but out of the box, it's not going to be particularly strong here. And we sort of saw some effects of that when we were building these models. We saw the logistic regression models did the worst of the models that we looked at. So they have a lot of nice features. They're pretty easy to interpret. They're easy to fit, but it's not the most flexible model type out there. So let's take a concrete example of nonlinearity. Let's suppose, I'm making this up, but let's suppose that there's the following relationship between age and functionality. So when a well first opens, it's pretty highly functional. Then after like a short period, the functionality starts to degrade. And then let's suppose that there's scheduled maintenance that starts to pick back up. And the maintenance schedule is such that the well declines, and then you replace some of the parts, and so the functionality starts to go back up. And then you replace more of the parts, so the functionality climbs back up to a high rate. So there's this very particular nonlinear relationship between the functionality of the well and the age. So in this case, this is an example of something that's nonlinear. So now I want to walk through a decision tree. The decision tree classifier was the second type of classifier that we used. So a decision tree classifier, what it's going to try to do is it constructs a binary tree where it's looking through all of the features that it has available to it, and is saying, if I were to make a split anywhere along this feature, and I were to put all of the examples that say are less than some value to the left, all of the examples that are greater than some value to the right, does that split make it such that to the left I've enriched myself in terms of zeros, and to the right I've enriched myself in terms of ones? Like, is that split effectively, I'm splitting on a feature, but it's also splitting the data with respect to the label and allowing me to like learn something about the data to make more accurate predictions on the basis of whether I'm on either side of that threshold. So in the case of a nonlinearity like this, decision trees can actually be really good. So if you had a decision tree, and this was all of the information that you sent to it, then you would put all of the training examples in the top. And what it would do is it would look through and it would say, so if the age is less than or equal to 1, so it's in this first bucket here, then I know with pretty high probability this is a functional well. And so that's maybe all I have to do is just say if it's less than 1, I already have a pretty good guess that it's going to be functional. And like that's the end of the game. If it's greater than 1 year old, then the decision tree has a more complicated calculus that it has to fill out because it has to account for what's going on with these other 4 buckets. So it's greater than 1. And so maybe the next thing that my decision tree is going to try to do is to pick off this high value. So it's going to say if it's greater than 5, then it's also going to be functional. So now we've picked off these top 2 values. And there's still another decision tree that we're going to build out for if it's between 5 and 1. And then that's going to recursively go down and say, OK, we already know it's greater than 1. We already know that it's less than 5. Is it more like 2 or is it more like 4? And on the basis of that, it's going to continue to subdivide the data such that eventually each one of these buckets will get its own part of the tree. And then based on which part of the tree any given future example falls into, we have a pretty good guess about what category we're going to assign to it. So this is an example of, again, a very simple, like single dimensional, or there's only a single feature that I'm putting in here. But this is something where a logistic regression will just fall flat on its face. And a decision tree does a lot better. In general, decision trees are, for my money, some of the best algorithms out there because they're pretty flexible. And they can handle some of these nonlinearities. They can handle interactions between different variables. In fact, I think this is my next, yes, this is my next example.
They work on continuous data, though.
Yes, they work on continuous data. Yeah, they work on continuous data. They work on categorical data pretty nicely. We still have to transform our strings into integers, but they're really nice. So this is an example of a interaction term. This is where there's maybe different patterns that hold in different parts of your data. That's what an interaction term is. So let's suppose that I have this nonlinearity that I have in age. This was the one that we saw before. But let's say that's only a pattern that I see in the southern region in Africa. And maybe there's a totally different maintenance program, let's say, that they're running in the northern part of Africa. Maybe they don't have a maintenance program. And so there's this pattern where things fall off the cliff really quickly and they never come back up. Or maybe in the western part of Africa, they have really great maintenance, and so you don't see things fluctuating around with respect to age the way that you do in other regions. So in this case, it's really helpful to know which one of these regions you're in, and then you can build out a subtree that figures out then what the relationship is between age and functionality. So that's what I mean by interaction term, where you have to know both the age and the region at the same time in order to understand, what the pattern is. So this is something that decision trees do really nicely. So the way this would look if you had a decision tree is it would just be a step deeper. And so this green triangle here is just the decision tree that we built out for the southern region before. But now there's a different decision tree that's now encoding the pattern that you have in the western region. There's a subtree over here that's the northern region. And so now the tree is starting to understand multiple different features and how those can play into the different patterns that you might have sort of all at the same time. Question? Yeah.
So, but for us, we just choose the algorithm and then the tree gets created.
Yeah, so that is like, yeah, so the question for those in the back is, so we can just pick the algorithm and it just does this. And the glib answer is yes. It's always, of course, a little bit playing with fire to just drop a machine learning algorithm in there because sometimes they can break in weird and funny ways. But scikit-learn is pretty disciplined about saying that they can be swapped in for each other. So this is, I think, both the wonder of scikit-learn and there's a little bit of responsibility that comes with it, I think. That's why I wanted to go through sort of what characterizes these algorithms. And I think that in general, I don't think necessarily, here's my own, this is my personal philosophy. You should feel free to swap in algorithms with joyous abandon. But if there's one of them that does particularly well, and you want to say this is the algorithm we're going to go with, stop and read the paper and try to really understand it. You're not going to understand every single algorithm out there. I've tried. It's a losing battle. But the stuff that you really rely on, you should understand it. And so for me, that's why I picked these algorithms to talk through. Logistic regression is really common. And then decision trees and random forests, we'll talk about random forests in just a moment, are sort of two of the algorithms that in most cases do really, really well. So these are good, solid fallbacks. But in any given case, each algorithm is going to be strong and weak in different places. So you do have a lot of flexibility to play around with it. But again, just if you're going to start putting any of these into production, I would encourage you to understand them first. Yeah?
So does scikit-learn let you specify, for instance, how deep or how wide that tree?
Yes. So the question was, does scikit-learn allow you to specify what we would call hyperparameters of the model? In this case, it might be something like how deep is the model or how wide do we allow the model to be. That was my next slide. So good timing. So for decision trees, this is one of the things that actually is not great about decision trees, if I'm being totally, well, arguably it's a weakness and a strength. There are many tunable parameters that are available to you in decision trees. Tunable parameters include things like how deep are you going to allow it to grow, how many examples do you have to have in one of these inner nodes before you allow it to split into two nodes. You can set all of these parameters when you're instantiating the classifier. So if you want to go back and rerun the code that you just ran, but with something like min sample split, this is set by default to 2. I'm just reading this from the documentation here. This is something that I just go back to the documentation for to remember. You set min sample split to 3 or 5, then you're going to get a slightly different tree. They'll have slightly different strengths and weaknesses. And this is one of the things that, again, is really great about decision trees is there's a lot of different ways that you can make them flexible. But it introduces a problem, which is how do you pick the best value? Depending on which one of these, depending on how you set the hyperparameters, that can actually change the performance of the algorithm a lot. And we're going to come back to this in just a few minutes and talk through like what are some concrete examples of what that might mean, and then some code at the end of the notebook that will that'll move through a bunch of different hyperparameter values in a way that is like actually really nice. But let me talk about random forest real quick before we get to that. So random forest is a really similar algorithm to a decision tree in some ways. Random forest just says instead of building one decision tree, build 100, maybe 200. You can pick. This is a hyperparameter that you can tune. And the general idea here is each individual decision tree might have some weak spots. And this is pretty typical, and it's nothing to be alarmed about. But if you have 100 of them, and you do something like you take the majority vote from all of those trees about how you're going to classify a given example, that's going to tend to be a better prediction that you get out than if you just had a single decision tree. In the same way that if I were trying to make some kind of decision about, like, I really hate clothes shopping, right? So I go with my friends, and then I ask them which shirt I should buy. And if I go with a bigger group of friends, then I have a little bit more confidence that if I get like a majority vote on buying a certain shirt, that's probably the right shirt I should buy. If I just go with my sister, then who knows what she's going to tell me, because she's just all over the map. So I bring my sister, but then I also bring like my sister's friends and my friends, and then they kind of balance each other out. That's sort of the idea of random forests, is that each one of these algorithms might be only slightly better than average, but when you take them all together, they can be a lot better than average because they're kind of voting on what the answer should be. So random forest, really similar to a decision tree in all respects because it's built upon that decision tree substrate layer. But in practice, it's actually has much better performance than a decision tree usually does on its own. And so you probably, if you look back at the cross-validation scores that you saw, the decision tree did markedly better than the logistic regression because it's picking up nonlinearities in the data, I suspect. And the random forest did even a little bit better than that. So we're seeing some of the theoretical like expectations that we would have of these algorithms actually being borne out in the data, which is kind of cool. Yeah, question?
I've heard that with random forests, oftentimes the trees that are built within the random forest are actually pretty small. They tend to try and keep them pretty short.
Yeah.
Stubby, as opposed to full big decision trees that are used in some of the
Yeah, that's right. So decision trees, one of the things about decision trees, this is a bit of a digression, but it's interesting and important, I think. Decision trees can tend to overfit. And what overfitting is where the algorithm learns very particular patterns that are specific to the training data. It basically memorizes the training data in a way that doesn't make it very good at making predictions on future predictions that it has to make. So we have, in this case, we'll get to this in just a minute, but there's training data and testing data. And usually what you do is you train your algorithm on just a subset of the data, and then you apply it to your testing set. And you say, how good was it on these examples that it's never seen before? And what happens when you overfit is your algorithm memorizes the training data, basically, and then it's not doing a very good job on the testing data because it's a little bit like over-tuned to those cases. And so one of the ways that you can protect against this with random forests is you make them a little bit shallower. You make them not as deep of a tree. There's other ways that with decision trees you can protect against it as well. This is one of the things that tuning the hyperparameters does also. So in general, there's a lot of ways that your algorithms can screw up. And that's why going ahead to the end very quickly and saying, like, how good is my algorithm doing? And then going back and retracing it in ways to try to make it better is, I think, in general, a better way to proceed than thinking about it very deeply and trying to optimize it in your first pass, because almost inevitably, there's going to be some surprises in there. So thinking about building these pipelines out iteratively, I think, is a much better, has much higher probability of success than trying to get it right the first time, because there's a good chance you'll end up overfitting or something like that. So a little bit about random forests are my personal favorite algorithm. We've talked about some of the ways that they're strong, so I won't belabor this too much, but I think for sort of an out-of-the-box classification problem, this is my go-to. You might disagree. You can have your own favorite algorithm. It's just a personal preference. But as someone, I mostly say this because I build machine learning models every day for a living. I've been doing it for several years, and I'm really lazy about it. I really don't want to be building models over and over again if they're not the best ones. And this is the one that I usually start with because it's very often the best. And even when it's not the best, the ones that are the best are usually slower. So again, sometimes I'll make small compromises in accuracy for algorithms that are easy to work with, and random forests are a good example of that. So we've done a lot of work at this point to get some machine learning stuff up and running, to get a gut check on what we've actually done and make sure that it makes sense. So I wanted to go through now some machinery in scikit-learn that makes all of this a lot more elegant and a lot easier to work with, and that is pipelines and grid search CV. So these are things that are particular. Some of the concepts are general, but a lot of this machinery is particular to scikit-learn. So I want to talk about feature selection first. Let me go in and find this stuff. OK.
Is this PowerPoint deck available?
Yeah, so the PowerPoint deck, there's a link to the Dropbox, or there is a Dropbox link that has the slides that is in the README of the Git repo. Yeah. So I want to go back to, we kind of sprinted through the first hour and 15 minutes here to try to get an answer as quickly as possible, and then I said we should go back and improve pieces of it. So the first piece that I'm going to improve is how we're handling the features that we send into this algorithm. And so one of the things that we did that wasn't ideal was, remember we had all those strings and we had to encode them as integers. And so the code that I wrote just looks at the categories that show up, kind of without any great logic to it, assigns each category to an integer, and then proceeds to make the transformation that way. But there's something that's not ideal about this, and that is that strings and categories are not ordered, but integers are. And as it happens, decision trees and random forests are actually pretty robust to this, but something like a logistic regression will really suffer from this if you have something that's basically categorical that's encoded linearly. So what I mean by that is that when we made this transformation, there was something like, let's say, sub-village, which is just a label that we've applied to some of these wells that we have. And sub-village, as it happens, has many different values. And I think there's like several thousand, actually, if you do the full mapping. And so there's some sub-village that happened to come out at the top of that list that was assigned to 0 or 1. And there was some other sub-village that was assigned to 3,924. And then everything else falls in between those two. But intuitively, there's no reason why any particular sub-village is 3,924 bigger than any other sub-village. It's just different. And so this is not going to be represented properly in the data if we just do that integer mapping. That's what I mean by saying that turning the strings into integers makes them look ordered in a way that isn't really true. So how do we deal with this? So the best way to deal with this is doing what's called dummying the data, or it's also called one-hot encoding the data. And so here's an example of what dummying data looks like. So let's suppose that what you had was, I'm using country here as an example. This isn't really in the data set, but makes it a little bit easier to think of, I think. So let's suppose that we have the first 6 rows of data here, and there's 3 different countries that we see showing up in our data set: United States, Mexico, and Canada. So if I were to integer encode this, I might put United States as 1, Mexico as 2, Canada as 3, remap it that way. That's what we did in the first part of the talk. But now that we are an hour older and much smarter, we're going to go through dummying it. And what dummying does is it expands out the data set. It makes it higher dimensional. And each different category that you can have here now gets its own column all by itself. And then there's an indicator variable that's going to be 1 if a row takes that data. And it's going to be a 0 everywhere else. So now the first row, which had been United States before, now there's 3 different columns that's like encoding the country information. United States is set to 1. The other ones are set to 0. And then likewise, like if you look at the last row there, Canada is marked as 1, and then United States and Mexico are set to 0. So in general, this is called dummying or one-hot encoding. This is a standard best practice for dealing with categorical data in general. And so this was something that we kind of glossed over the first time, but now we're going to go back and clean it up. So there's a few different ways that you can do this. I used a scikit-learn one-hot encoder, but there's also a function in pandas called getDummies that works pretty well for this too. So I think that this is code that I gave to you rather than asking you to write it yourself. Oh, I did ask you to write it yourself. OK, cool. So this will be fun then, because I'm sure you're getting a little bit tired of hearing me talk. So you can use one-hot encoder. You can use pandas getDummies. You can code up your own scheme for this if you like. But in general, what you want is some kind of function that you can pass in the data frame and the name of a column that you want to dummy. And it'll give you back the same data frame, but now with that column expanded out. So let me give you about 10 to 15 minutes to hack away on this. In my experience, it actually takes a little bit. Like, if you know exactly where you're going, you can probably do it in 10 or 15 minutes. But in the interest of keeping things moving, that's kind of all the time we'll do for it here. And then I'll go through the answer. So don't freak out about it too much if you find yourself a little bit rushed on this one. But take a few minutes and try to think through how you would go through dummying an arbitrary column here, again, using one-hot encoders, using scikit-learn, using pandas.getDummies, and then keep in mind that the solutions are there if you get really stuck. So take a few minutes and start thinking about that now. OK, so quick show of hands. How many of you have a one-hot encoder working, or you feel like you're within a few minutes of it working, maybe? A few. And then how many of you are still working but are not stuck? A few. And how many of you feel a little bit stuck? OK, not everyone is raising their hand, but that's all right. OK, so I think we'll, in the interest of time, kind of keep going. If you're struggling a little bit with this, it's actually, this is something that I struggle with too. in a way that I just want to like say with full candor, sometimes it's easy to feel like this is harder for you than it is for everybody else. That's the way that I felt a lot of the time when I was learning. And in all honesty, that is sort of the way that I feel right now. Still, very often, there's stuff that seems like it should be pretty easy, like, oh, I just need to take this column and like flip it on its side and dummy it out. And sometimes it takes a lot longer to figure that out, either because it's conceptually a little bit challenging or because sometimes you're fighting against the algorithms themselves a little bit or their particular implementations. So I just say this by way of reassurance that even though sometimes it looks easy, it isn't necessarily. That's one of the value of coming and sweating a little bit in these workshop settings is you kind of get some of the tough implementations out of your system so that the next time you do it, it's a little bit easier, hopefully, for you. But total candor here, putting all of this code together and getting it to work took me like a week. So again, if it looks easy, that's a little bit of a sleight of hand. So don't be discouraged if it's taking you more than 10 or 15 minutes, because it probably took me more than 10 or 15 minutes. And we kind of just can only take 10 or 15 minutes to do it right now, so we can keep going. But slight pat on the back if you're feeling like slightly overwhelmed. This is why we have the answers, and y'all are doing great. So as I was making the rounds, there was a really good question that came up, and that's actually what I wanted to talk about in the next part. So when you're dummying, it comes at a cost. So we talked through why you want to do this, because it's actually a better way of representing categorical data. But the cost that it comes with is that as many different categories as you have in a given column, there's going to be that many columns in your new data set. And I don't know if, for those of you who got this working, if you dummied out something like sub-village, or I think water basin is another example of this. There's columns in here that have lots and lots of different unique values, because it turns out there's just lots and lots of sub-villages in Africa, and they recorded the name of them for each one. And so sometimes you can end up in a not very ideal situation after you've dummied, where you have extremely high dimensional sparse data. And we're not too far into the danger zone in this case. I think if you dummy everything out, it takes on a few thousand columns, which is still within the realm of what we can deal with on like the memories of our laptops here. But you can imagine for data sets that can be much more diverse or that are much bigger, this can blow out the memory on your machine really quickly. So there are certain types of algorithms that are just robust to this, and if this is the type of data that you work with, it's worth thinking about machine learning on sparse data as its own concept. But for us, the thing that we're going to do is take a little bit of a hacksaw to it now and reduce the dimensionality back down. So we started out with something like 40 or so columns. We've now, if we've dummied everything, blown it out to several thousand. As it happens, in this notebook, there's a bunch of columns that I remove in the next cell. I just get rid of them, because if you dummy them out, it's so bad that it's kind of like not worth the trouble. So I got rid of funder, installer, sub-village, all this kind of stuff. This is admittedly probably not ideal. And if we had a lot of time to really go into those columns and try to understand a more optimal way of figuring out how to deal with them, that would be not a bad use of our time. But we're going to do something that's a little bit simpler than that now, which is doing feature classification, or sorry, feature selection. So this is another thing that I will have you do, but let me talk about it just briefly here. So feature selection, the idea of feature selection is we have, let's say, 4,000 features. That's more than we want to deal with when we're actually doing the machine learning. There's a lot of reasons why machine learning algorithms usually don't do very well with very high dimensional data. The biggest of which is that it tends to make you very prone to overfitting. We talked about this a little bit before. So it's hard to make models that generalize well to new cases on very, very high dimensional data sets. So that's not ideal. And also, it's just a lot of very heavy memory footprint to be carrying around if we have 4,000 features. So as an exercise in dealing with this, we're going to go through a feature selection process. And there's a bunch of different ways that you can think about which features are the most important. But the general idea here is that not all features are created the same. So there might be some features that are really, really important for understanding which wells are going to be functional. And then there are some features that probably don't tell us anything particularly interesting, and we want to have some way of splitting our data set and picking out the ones that are going to be helpful and getting rid of the rest of them. And so as you can imagine, there's a bunch of different ways that we can define like what a good feature is and how we would go to look for them. But this is one of the simple examples that's in scikit-learn. It's called select k-best. And this is not the most sophisticated thing that you could think of, but it's a good first pass. And what select k-best does is it just goes through each of the features individually, and it says how predictive of the outcome that we're interested in is this feature just by itself. And then it sort of stack ranks all of the features relative to each other, and it picks off the top k, and you have the freedom to specify what k is. And I forget what the default is, but what I've done in this example is maybe like 100 would be a reasonable value. I don't exactly know, but like, sure. We're going to revisit this in a little bit. But the general idea here is that before we're going to send in this 4,000 column data frame, and after we apply select k-best, we're going to get back 100 features, which is nice. I'm going to have you code this in just a moment, but there's something that I've glossed over that's really important, and I want to come back to it before we go too far, which is that in general in machine learning, there's the idea of a training and a testing set. And we've been a little bit glossing over this. But the idea is that the training set is a subset of your data that you set aside for actually having the algorithm learn what the patterns are. So the algorithm itself, like the decision tree, for example, is going to build out all its binary splits on the basis of that training data. So it knows the answers for this training data, and then it knows all the features and is trying to find the relationships between them. But what you're really interested in is not how good your algorithm is going to be at predicting examples in the training set, because it can get really good at those if it memorizes them, but that's not necessarily a great model. You want to know how well it's going to do on a new example, a new like row in your data set that it's never seen before. And that's what the testing set, that's the role that testing set serves. So testing set is part of your original data. You have labels for it. It comes from the same source as your training data, but you hold it back when you're training. You don't use it when you're training the algorithm. And then after you've trained your algorithm, you send your test data through it without the labels applied, and you ask your algorithm, what's the prediction you would make for all of this, all the data that I'm sending through? And this is going to give you back a bunch of predictions. And because this came from the same data set that your training data came from, you have the answers. And so then you can compare the predictions to the true answers. And that's going to give you a much better estimate of how good your algorithm is going to do on new unseen data than if you were to look at something like the training data. And so this is sometimes also called like the out of sample predictions or the out of box predictions. I like to sometimes you call it validation data set. There's several different terms here, and they all mean sort of the same thing. But the general idea is that you want to be disciplined about splitting up your data at the beginning of the exercise in such a way that your testing data, you don't look at it until the very end. And so this is something that we've been a little bit glossing over, but we sort of haven't been. So as we've been building and evaluating these algorithms, we've been using, you might have noticed, this thing called cross-val score. So let me go find the example of that, this cross-val score. And so cross-validation is something that's really similar to a training and testing split. What makes cross-validation slightly different is it'll split your data into usually like 5 to 10 pieces. I think in this case it splits it into 3 pieces. And it's going to train on, in this case, 2/3, and then test on 1/3. And then it's going to cycle through and pull out a different third of the data, train on 2/3, test on 1/3, And it cycles through that 3 times. So every example that you have in your training set is going to be, every example that you have in your sort of big data set will be trained on twice and tested on once. So it gives you a chance to see all of the data, but you're still getting good representations, good estimates of how your algorithm is going to do on new unseen data. So cross-val score already does sort of this training, testing, split, and bookkeeping under the hood. And then what it does is it calculates the scores on all of the testing folds. And then, well, in this case, it doesn't average them together. It just prints all of them out. That's why you get 3 different scores in the pieces of code. Here, let me show one with the answers. When we were building out the algorithms a little bit earlier, there's 3 different numbers that you get out. That's because cross-val score has this sort of 3-fold split going on under the hood. So it comes up with 3 different answers, and then you can average them together or whatever if you like. I haven't bothered to do that here, obviously. But I find that cross-val score, it's not like the most sophisticated way of validating your model. Scikit-learn has, in my opinion, better ones. But it's really fast. It's 2 lines of code, and it just works. So that's why I've elected to use it for this part of the talk, because it gets you like in the neighborhood pretty quickly, which I appreciate. So again, probably something that you would, if you were going back and had to build a maintainable like model that would stick around forever, you might use something that's a little bit more robust and controllable than this. We'll talk about this a little bit later in the afternoon. But for those of you who are a little bit nervous by the fact that we didn't have training and testing sets, because you've done this before and you know how important they are, fear not, we actually did. So we can trust these scores. They are giving us good representations of what our models are going to do on new unseen data. So select k-best was what we were talking about before. And this is, do I have it here somewhere? No, I thought I did. Here we go. So I'm now in the end-to-end workflows using pipeline and grid search CV. If you're a little bit lost, it's like the first code block under there. So a little bit switching our focus back to feature selection. We're moving into the part of the talk now where we're going to start pulling some of these pieces together. And so the first one is like, we want to have some feature selection. We've dummied out the data set, and now we want to go through collapsing it back down. This is another good opportunity to get your hands on the keyboard here. So select k-best, again, is just a class that you can use in scikit-learn. And I'll put up the answer a little bit, but again, like only look at it if you want to. And take a few minutes to actually code up a feature selection and check that it's reducing the dimensionality of the data after you've had it blown up with all that dummying we just did. So we'll take maybe 4 or 5 minutes and do that now. Okay, so I think I'm going to keep going. We're going to power on through for maybe 10 or 15 more minutes and then take a 15-minute or so stretch break for those of you who are feeling a little under-caffeinated or what have you. So stick with me. We're almost at the intermission here. But let me just show you, guide your eye through this code a little bit here. Again, really fast and easy to do this stuff in scikit-learn. And the main thing that I wanted to point out to you is that after we've transformed our data using select k-best in this case, I'm printing out the shape of the data set, which basically tells me the dimensionality. So we have 59,400 examples in this data set. As it happens, that's been the same the whole way through. But now it has 100 columns in it, whereas before it was something like 3,000. So this is just a little bit of like a good gut check that select k-best has actually reduced the dimensionality of the data set. It was sort of pointed out, and this is a little bit of me sweeping things under the rug. It turns out that select k-best doesn't really improve our models that much. As it turns out, decision trees are pretty robust to, or in random forests especially, are reasonably robust to high dimensionality. Also, they're a little bit robust to the dummying stuff that we talked about before. So select k-best is making them stronger in a place where they aren't particularly weak. That's maybe the way to think about this. But one good reason that you would do dimensionality reduction, even if it doesn't improve your model, is to make it more interpretable. So if there's a 4,000 feature decision tree that you're going to try to explain to someone, like what is the logic by which we classify wells, like if there's 4,000 variables that you have to be thinking about in describing that, like that's going to be really challenging. I don't know that 100 is really that much better, but if you get it down to maybe 5 or 10, that's actually pretty interpretable. Like decision trees make sense to a human, which is one of the things that's nice about them. So dimensionality reduction, even if it doesn't improve the model, can sometimes just make things a little bit more stable and maintainable. So this is another good thing to keep in mind, even if you don't think you strictly need it for performance. It can just like make your life better in that aspect. The other reason that I had us do select k-best is it gives me a reason to talk about pipelines, which are maybe my second favorite thing in scikit-learn. My first favorite is grid search CV, and we're going to get to that next. But pipelines are a special construct in scikit-learn. And the idea of a pipeline is that you have multiple different pieces of scikit-learn machinery that you might want to string together one after the next, and then have it fit all of that at the same time instead of you having to fit each one of them manually and kind of manually pass the data from piece to piece. So I'm going to show you a little bit what this means, but let me talk a tiny bit about pipelines and how this works. Oh, I lost a slide. Whoops. OK, anyway, that's OK. So the idea of pipelines is there's kind of two different types of objects in scikit-learn. We're going to talk, this is just a little bit of scikit-learn like minutia. There's what's called transformers, and there's what are called estimators. And so select k-best is an example of a transformer. What transformers do is they change your input data in some kind of way. So dimensionality reduction is an example where it's going to pare down your input data. And so the way that you can tell a transformer is it has this transform method associated with the class. These are different from estimators. Estimators include things like logistic regression, decision tree classifier, random forest classifier. These are the things that we think of as machine learning algorithms. Estimators, what they're trying to do is take a set of data and predict a set of labels from it. They have a very clear vision of kind of what their inputs are and what their outputs will be. Transformers are a little bit more about like how do we want to change the data to make that process easier or more successful. And so the idea of a pipeline is you can string together as many transformers as you want, one after the other, into a pipeline. And what a pipeline will do is when you fit the pipeline, it will move through and transform, do the fit transform on each of those in succession in kind of like the way that you think it should, which is just nice that there's this very intuitive piece of machinery here. So n number of transformers, as many as you want. And then at the end, optionally, you can have an estimator. So this is like your machine learning algorithm that comes at the end of doing all of this feature transformation. So in our case, the pipeline is going to be a pretty simple one. We have one transformer, which is select k-best. And then we're going to have an estimator, which is a random forest classifier. And what I want to do is instead of having to fit select k-best, get the data out, then turn around and stick the data into a random forest, and then get the predictions out, I want to just say there's a pipeline that's select k-best and then random forest, and just take care of it. And that's what pipeline does. So let me show you the code for actually doing a pipeline, because I think it's a little bit, I always just have to go back and look at Stack Overflow to remember what the syntax is here. It's not that hard, but I just never remember it. But the idea is you make, first of all, you have to import it from scikit-learn. You import a pipeline. And then you have to instantiate each of the steps that you're going to have in it. So you're going to instantiate your select k-best thing. You're going to instantiate your random forest classifier. And then you put those into a list. There, you make tuples of those. You stick them into a list. And then you can stick that list into a pipeline. And then scikit-learn knows that they're strung together like this, and it can sort of treat them as one coherent unit instead of as individual pieces. And so then instead of having to fit them individually and mess around with transforming the data and all this stuff, I can just do like the fit and the fit predict on the pipeline instead of on the individual objects. So that's what I'm doing in this last part down here. I'm actually fitting on the pipeline now instead of on my random forest classifier. There's one other thing that I've changed here too, which is we talked a little bit about cross-val score and how that's like a poor man's like train test split. So I'm now using kind of the more canonical training testing data splitting machinery in scikit-learn, just because I think it's important for you to see that at some point. But there's sort of, you can still have pretty good success with cross-val score if you want to stick with that. And then the last thing I'm doing now, I'm fitting my pipeline. Again, it just takes a couple lines of code. And I'm printing out a slightly more informative set of performance metrics than I have been so far. So up to this point, I was just saying there's this cross-val score. 0 is bad, 1 is good. And that's kind of all we said. But now I might be interested in asking more specific questions about where my model is weak and where my model is strong. And so classification report is another piece of machinery that allows you to get a quick, get your bearings quickly. So let me just walk through real quick what each of these metrics do. Before I do that, is there a question?
Yeah. So when you talk about fitting the whole pipeline, does
Yeah.
that mean that it will do the segment case that predicts k-best in a way that optimizes the downstream algorithm as well, rather than find the k-best in an algorithm diagnostic way?
Yes. So the question was, is there any optimization that's going on inside of the pipeline fitting such that maybe there's a select k-best that with foresight would be a better select k-best in anticipation of the random forest that we're going into, but that wouldn't be obviously apparent to me like when I'm fitting select k-best on my own, if that makes sense. And in general, no. So a pipeline doesn't have any sense of like optimizing everything together, at least as far as I'm aware. It sort of treats them as atomic units. But there are places where there are like interactions between the way that you fit select k-best and then what happens in random forest and like what's going on there. And that's what we're going to get to in grid search CV, which is my #1 favorite thing about scikit-learn. But before we get there, let me just go through classification report real quick, because this is now giving us a more fully flavored picture of what our model is doing. So this is now giving us several different numbers instead of just a single score. So what are these? So first of all, there's 3 classes. That's what the 0, 1, and 2 are. So you might remember that 2 is functional, 1 is functional, needs repair, and 0 is non-functional. And so starting from support, because I think this is the easiest to understand, support is just how many instances of this did I see in my data set, or in my testing set. So in particular, what you might notice here is this is a pretty severe imbalanced class problem. We hadn't really talked about that so far, but there's over 10,000 functional wells, and there's less than 1,500 functional needs repairs. So this is something that can be pretty challenging, actually, for machine learning models to handle. It's easy for them to overlearn the patterns in the majority class. So this is something we'll have to keep a little bit of an eye on. But for a first pass, it's maybe respectable. Precision. So precision, let me just pull up the slides for this because I always have to check myself and make sure I'm defining these all correctly. Yes, okay, so precision. So for each one of these classes, we say there's such a thing as like a positive example of this class. So like how many instances are we predicting to be in this class that are actually in this class? That's what a true positive is. Divided by what's the number of true positives and false positives. So what precision is basically saying is of all the times that I said a well was non-functional, how many times was it actually non-functional? Do I have like a 50% success rate of being correct when I say a well is non-functional? Do I have like an 80% success rate? That's what precision is. So saying that we have an 80% precision of class 0 means that 80% of the time when we have a truly non-functional well, or no, excuse me, 80% of the time when we say a well is non-functional, we are correct. That is precision. recall is the thing that I almost said instead. Recall is of how many true broken wells, how many of them are we actually predicting as broken. And so in this case, 56% of them are correct. So we're getting about half of the actually broken wells are we predicting. And then analogously for the other categories, obviously. And then F1 score is a combination of these two metrics. So there's always going to be a trade-off between precision and recall. It's kind of like, what kind of mistakes are you willing to make? If you want to have a really high precision, if you want to say, I'm very certain every time I make a prediction that it's actually a broken well, then you're going to incur some cost. You're going to be more cautious about saying that you think a well is broken because you don't want to be wrong about that. But that means that your recall is going to go down. It means that even if there's something that looks like it's probably broken, you're not going to identify it as broken because you don't want to make the mistake of like being wrong in that way. And then vice versa. Like if recall is really important to you, if it's really important that you get as many broken wells as possible flagged, your recall will be higher, but your precision will be lower. There's going to be some stuff that you think is broken, but it's actually fine. So there's always going to be some trade-off between the two of those. An F1 score is like a geometric mean or a harmonic mean of the two of them, so that you can hopefully get a little bit of a balance between the two. So depending on the context of the problem, we don't really know how bad it is to make each of these kinds of mistakes in this context, but usually when you're actually solving a problem in practice, you do have some opinions about what kinds of mistakes you want to make. So precision, recall, F1 score, which one of these you pay attention to can vary just depending upon the context. So now let me push through to Grid Search CV. Grid Search CV. I love Grid Search CV. So we've been talking a lot about how a lot of these algorithms, we have tunable parameters, and a priori we don't necessarily know what values they should take. So tunable parameters might be something like, how many features should we select in our select k-best? Should it be 10? Should it be 50? Should it be 100? Should it be 1,000? I have no idea. And I'm like, even if I were to think about it really hard for a while, I would probably not be right. The best way to answer this question is to try a bunch of them and like pick the best one. Similarly, with random forests, for example, we know that decision trees have a lot of parameters to them. Random forests are made of decision trees, and so random forests have a lot of different parameters that we could try. And again, I don't have a good intuition necessarily for which one is going to give me the best answer in any case. It's just going to depend on the situation. So what I want to do is I want to try a bunch of different values, and then I want to pick the best one. And so what I'm starting to do is think about a model fitting procedure in which I'm actually fitting many different versions of each of these models that have different values for the hyperparameters, and then picking the best one of all the ones that I find. And in particular, I don't want to do each of them independently. I mean, I can. It's not a terrible idea. But if I really want to be thorough about it, I want to go through all the different combinations that I can see of each of the different hyperparameter settings that I might have, because as we said before, sometimes there's interactions between what happens in select k-best and then what happens downstream in random forest. And so you want to be able to allow those two axes to move independently of each other so that you can understand, sort of how one step might affect the next. So now we're talking about potentially a very large decision space that we have to scan. That's kind of what this picture is each one of these boxes is a different hyperparameter setting that I might think of as totally reasonable. Each one of these would be a model that I have to fit in order to understand which model of all the different options here is the best one. And obviously, this is just 2 dimensions of what's potentially a very high dimensional hyperparameter search. So this is even kind of an oversimplification. And I have no idea necessarily where in this grid I'm going to find the right answer. So what Grid Search CV does is it basically takes you can use it on just a plain algorithm, like a estimator just by itself, but you can also use it on a pipeline. And what Grid Search CV is going to do is it's going to multiply out that big hyperparameter grid, and then it's going to systematically move through, fitting a different model for each point in that grid. and then return to you the best one that it finds. So this is going to take a long time. When I actually ran this code on my computer, I waited for it to finish for a while, and then I went and cooked dinner, and then when I came back, it had finished. So this might be a good thing if you're still sort of tracking on the notebook to start this last block of code running and then go take a break, and maybe by the time you get back, it will have finished because it's making like whatever, 50 different models potentially. But what I'm doing here is I have a few different values of k that I'm trying. I've picked 100 and 200, but feel free to insert whatever other numbers you're interested in trying. The number of estimators in my random forest, so this is basically how many trees are in my random forest. And then the min sample split for random forest. So within each of those decision trees, what's the minimum number of samples that I have to have in a node before I will allow it to split? So each of these is going to control different aspects of what makes this algorithm strong or weak. And I want to try all the different parameters. So I won't go through all of the syntax here for exactly how you set up a grid search CV. This is another thing that, quite frankly, I just look up every time I have to remember how to do it. But the long and short of it is that you declare this parameter grid that has all the different parameters that you want to scan and the different values that you want to look at. And then you send them into this grid search CV object along with the pipeline. So this is the original pipeline that had a select k-best, then chained onto a random forest. And then you take your cross-validation object and you fit that. And this is going to do sort of under the hood all of that big combinatorial expansion, fit all the models, and then at the end collapse them all back down and give you back the best one. So within all of the values that we're scanning here, we'll get the best hyperparameter combination. And then I'm having it print out the classification report for this. So feel free to monkey around with that a little bit. And like I said, if your computer is anything like mine, it's going to take a while to chew through all the models. Of course, it depends a little bit how long on how complex you want to get with your parameter grid up here. But I promised you all a break, and I try to keep my promises. So let's take about a 12-minute break and come back at 4:20 or so, and then we'll move into the second part of the talk.
Get a sense of what was selected in
Sure.
that, because it returns that array or matrix doesn't have any column
Yeah.
names. Like I don't even know what I'm looking at.
Excellent question. So how do we know what features it selected? So my answer to most questions about scikit-learn, how do we know fill in the blank, is we go to the documentation. So let me live dangerously and try to use the internet right now. So select sklearn, select k-best. In general, after you've fitted a lot of these, the estimators, the transformers, whatever, they have attributes that will tell you usually the things that you're most interested in knowing. So in the case of select k-best, it's like, what did you actually select? Apologies that this is taking so slow. Looks like the internet is being a little bit slammed right now. So while this is coming up, I'm going to stall for time here a little bit and hope that it comes up. But the short answer is I don't know the syntax off the top of my head. This is one of the things, I feel like, okay. This is one of the things that I would go Google for. And then the documentation in general, like I said, is really good and will help you out. So maybe now that I've been rambling here for 30 seconds or a minute, if any of you have been Googling alongside this and have the select k-best documentation successfully pulled up and want to shout out the answer, we could probably come up with. Yeah.
There's actually a best params. So if you just type in CD and then press shift, you can actually select one for best params, and it shows you what the best k value and estimator and all three of those.
Okay, so let me repeat that. I think it's an answer to a slightly different question, but it's a good one. It's a good one to call out. So in the case of grid search CV, we might ask the same question of grid search CV, like what were the best parameters that you found? And in the case of grid search CV, there's an attribute called best params that will tell you what was the winner. In the case of select k-best, it's probably something like features or classes that you would get back after you fit the object if you ask for it. There's some code that starts to get to this. Okay. This starts to get to this a little bit for a different piece of scikit-learn machinery. I'll try to point it out to you. But in general, I would go check the documentation and then look for something that looks like what I want. And I'm sure that for select kbest it exists. I just don't remember what the syntax for it is off the top of my head. But good question. Yeah, another one.
Do you have, as any of the data reports on data camp?
Is any of the data for this on data camp?
No, I'm saying if anything that's on data camp or, relevant or helpful to learn.
Oh, other resources for learning this stuff. Sure. So like I said, I'm a little bit biased because a few years ago I did a machine learning course for Udacity that covers a lot of this material, and in particular goes into the algorithms in more depth and breadth than we have the time to do tonight. I think you're able to register for that completely free, although it's been a little while since I've navigated the Udacity website. But the name of that is Intro to Machine Learning. And again, that's just Udacity. So that's my first answer. My second answer is there's a lot of other good resources, and which one you want to go to next a little bit depends on what you want to do. If you want to understand the math of machine learning more, then Coursera has an excellent machine learning course by one of the professors there. I think it's just called Machine Learning, and it's had like 3 million people take it at this point. It's super famous. That's a really good introduction to the math, which we are obviously glossing over here. DataCamp is really good because you get to get your hands on the keyboard very, very quickly, and you kind of learn by going through exercises. And then there's a lot of really good blogs and tutorials and things like that. I don't have like a clear favorite amongst the many good ones, but there's a lot of people who've put a lot of time into writing nice like IPython notebooks that go through some of this stuff in a lot more detail. And then maybe the last example is once you get a little bit more comfortable with scikit-learn, if that's something that's new to you, the scikit-learn documentation is so good that I think of it as actually a really good educational resource. So they have a lot of good examples on there and code snippets and things like that that you can start to get a sense of the realm of the possible, as I like to say. Really good question. Yes, another one? Is IPython Notebook equivalent to Jupyter Notebook? Yes. Okay. So they were called IPython. It was called IPython for a long time, and then I think a year or two ago got serious about calling it Jupyter. The reason being that we're using this notebook for Python, but you can also use it for R code, for Julia code. That's where Jupyter comes from, is Ju-Py to R. So those are like sort of the original Three Musketeers, but I think it actually has kernels for a lot of different languages. So if you're, for example, much more comfortable in Java and want to use some of those machine learning libraries, there's probably I'm almost certain there's a Java kernel that you could get up and running. So yes, yeah.
I guess after responding to that, I guess I'm a little confused as to why do we, how the pipeline is connected to the grid search, because in the grid search, one of the parameters were you put in different k values, right?
Yes.
So then what was the point of the pipeline then?
Oh, so the question is what's the relationship between the pipeline and the grid search? So when you make the pipeline, you have to instantiate those. So let me pull it up to be a little bit more concrete what I mean. So when you instantiate your select kbest and your random forest classifier, those are going to have some parameter values by default, or in this case, we've set a parameter value k equals 100 or whatever. The grid search CV will kind of ignore this stuff and just go through and say what are all the different hyperparameters that I want to try. So it kind of has to have them in order for them to even be like well-defined existing objects. But the grid search CV is really driving with respect to what parameter values it tries when you're using that machinery. Does that answer your question?
So how do sorry, I still don't understand.
No, that's okay.
So how do we, so here we put k equals 100, and you're saying in the grid search we don't actually, because the only part where I see we use pipeline is when we actually put in the grid search CV when one of the parameters, but it doesn't exist in the actual dictionary, like the parameter dictionary.
The k equals 100?
Yeah.
Yeah. So if we were to just run this pipeline right now, it would.
Or like the reverse. What if we just run the grid search without the pipeline and just do the random forest with the grid search? You can do that?
Yeah, so you can run a grid search CV just on an estimator all by itself. Yeah, absolutely. Yeah.
Okay, and the reason we did this is?
And the reason we did this was that was a little bit of fancy footwork on my part, just to show that you can do it with potentially several different pieces at the same time. But if you go in and find like some of the out-of-the-box examples they have in scikit-learn are just optimizing, for example, the random forest classifier by itself. And you don't have to necessarily optimize select k-best, but you have the option to if you want to. Yeah.
Thank you.
Sure. More questions? Yeah.
So you're talking about how you normally start out with random forest classifier. Can you give like an overview of how you choose like which models you want to test?
How do you choose which models you want to test? That's a really interesting question. Again, a lot of it is kind of experience. And the reason I like random forests is just because I've done this a lot, and it usually does pretty well. And it does well quickly, which I like. There's other algorithms that, if I want to wait around for them, will probably win slightly over random forests. But random forests are usually like pretty good, like bang for your buck. Which algorithm I want to use really depends on, I think, what I want, how well I know the data set that I'm looking at, and in particular, what kinds of relationships I think might be in the data. So if I think there's a lot of nonlinearities, if I think there's a lot of interaction terms, that nudges me toward something like a decision tree-based algorithm. If I think that there's probably a lot of linear relationships, then I might use a linear model. For me, it's a little bit more driven by a trade-off between interpretability and predictive power. And so this is something that's generally true in machine learning, is that the algorithms that tend to do the best generally are the hardest to understand. So this includes things like random forests. A decision tree alone might be not that hard to understand, but 100 decision trees all at the same time is like a little bit challenging. Gradient boosted trees is another type of ensemble algorithm that's based on top of decision trees. Very hard to understand. Neural nets are like maybe the worst example. Like, God help you if you have to interpret a neural net, but they can do amazing things in certain contexts. And so for me, a lot of times, the thing that I'm thinking about is not necessarily what algorithm, what's going to get me the best accuracy here. It's going to be, what do I need to do with this model? And in particular, do I need to explain this model to somebody else? So there are certain models that the reason we're building them is because we want to understand the relationships that they're trying to model. Like if I have, for example, this was something that came up in work recently. We have customer churn that we're predicting, right? And so our clients who are trying to understand why their customers are churning, they want to know why. So they want to be able to interpret the model, like what are the features that are the most important? Are they nudging people towards churning or away from churning? And this is a pretty thorny, like statistical issue to unpack, but at the end of the day, I'm not going to be able to answer that very well with a neural net because it's going to be very obtuse how it's making the predictions. It's going to be doing something really intricate and complicated and hard to understand. A linear model is something that's going to be a lot more interpretable in that case. And so that's going to be like my algorithm of choice if I have to explain it. So yeah, it's a little bit counterintuitive, I think, sometimes when you're getting started because you spend a lot of time thinking about which algorithm is the best for accuracy. But I find that usability and interpretability is often higher. And risk.
Risk of being wrong.
Risk of being wrong, yes. And that's another point, is that you might have two different algorithms that are appear to have similar accuracies, but they might be making mistakes on different types of classes. And so you might have certain types of mistakes that are very, very expensive and other types of mistakes that are no big deal. like what's a small example? Fraud detection, right? If somebody steals my credit card and they run up a $10,000 tab on it and like my bank doesn't catch that, that's a huge problem for me. Whereas if I go and make a purchase that's like anomalous for me, I go out and buy a washing machine, and actually this happened to me a couple months ago because I had to buy a washing machine, right? I'm putting $1,500 on my credit card to Best Buy, and I never shop at Best Buy. And it didn't let the transaction go through initially because it was an anomalous purchase for me. And in that case, they say like, of course it's not ideal that I have to, text my bank and say like, yes, I actually wanted to make this transaction. They just sent me a text and said like, was this you? And you just say yes. So that's not ideal. I don't really want to have to do that, but I would much rather have to do that than have somebody successfully buy a washing machine with my credit card and have me be like stuck paying for it, right? So that's an example of like how different kinds of mistakes can have different kinds of costs associated with them. And so if you're in a regime that's like that, where certain types of mistakes are much more or less costly, then that's something that you might even bake into the model that you're building or the way that you're making decisions on the basis of the predictions of that model. It's a really good point. Yeah?
You mentioned neural nets. Does scikit-learn employ neural nets, or is it something?
What about scikit-learn and neural nets? Yes, so scikit-learn is more traditional machine learning. They've made, I think, a conscious effort to not get into the neural net space because it's just so big and they want to keep the boundaries well defined. So if you're using Python and you're interested in neural nets, there are some other really good packages for that. TensorFlow is getting a lot of attention these days. Theano also has a lot of market share. And then there's a library called Keras that can actually sit on top of TensorFlow or Theano that makes them a little bit easier to interact with. So if that's something that is interesting to you, that's where I would go look for the neural nets in Python. Good question. Any more questions before we keep going? OK, cool. Well, thank you for all of those questions. Those were really interesting. So we have about an hour and 20 minutes left. And in my naive enthusiasm, I thought we would have like 3 hours left at this point. So I think what we'll do is I'm going to be a little bit judicious in the hands on the keyboard parts. I'd still like to try to get 1 or 2 things where you get your hands on the keyboard, but it might be a little bit more of me talking. In the interest of getting to the stuff that's at the end, because I think the stuff that's at the very end is the most interesting. So let me just acquaint you lightly with the machinery now. We're not going to be using the Jupyter Notebook anymore. The rest of this is going to be in a text interpreter, so Sublime or Vim or Emacs or whatever your text editor of choice is. Excuse me. And so the whole point is we're going to be taking sort of that workflow that we just prototyped out. Like we're going to do the dummying, and then we're going to do the select k-best, and then we're going to do the model pipeline thing, and we're going to fit that all. But we're going to try to do it in a way that's a lot more robust to somebody else using this. So Jupyter Notebooks are a good place to get started, but they're hard to maintain. And if, for example, we got a new data set in and realized that it broke the notebook, then it would be really hard for us to fix that in a way that would be consistent with the data set that we already have. And just in general, we're moving in a step that's more like this is machine learning software instead of just I hacked some stuff together in a notebook. So to that end, what I've done is try to build it out incrementally in steps. And each of the steps are in the slides, sort of what we're doing and why. Some of these will move through a little bit quickly, just so we can keep going. But there's 16 steps in all, and each of the steps I have the solutions for in the folder that's in the Git repo called solutions. So if you kind of move through those in sequence, each one builds upon the last. And so if at some point there's something that feels like we went through it a little bit faster, or you didn't totally get it, or you would like to try it on your own, but like we didn't have the time to stop and chew on it, feel free to peruse this code later. It should be reasonably user-friendly, although it's not perfectly clean code. It's pretty good. And like I said, we'll move through this fairly quickly so we can get to stuff like testing and model comparison at the end. So with that, let me remind you just briefly of kind of the scenario. So we've just come up with a reasonably good solution to the problem of how do we predict which wells are going to fail in Africa. That's great. Let's suppose that there's now a team that's out in Africa that is incrementally using our predictions to go out and inspect wells. And as they're making those inspections, they're collecting more data and they're sending it back to us. And that maybe they're not speaking to us directly, but there's some kind of non-technical intermediary. We need to make the modeling workflow something that a non-technical person could use as easily as possible. And in particular, they might have some questions like, where is this model strong? Where is this model weak? If we go out and collect more data, has that improved our model? Has it improved our model because the new data is different, or because we just got more data and then like the model gets stronger everywhere? So these are really important questions, and these are the kinds of things that I find myself having to answer all the time about the models that I build. But it's comparatively, I think, much harder to build software that makes it easy to answer these questions than it is to just come up with a workflow for the first time. So that's what I wanted to talk about in this part of the talk, is walking you through a little bit the way that I've rewritten this problem so that it's a little bit more robust. I think if I were to go back and spend another couple days on this talk, could very easily see myself rewriting it yet again, because there's some stuff in here that turned out to be a little bit harder, and I had to do like more convolutions than I expected. So even this code is probably not God's truth best code, but it is going to be something that's pretty maintainable compared to the notebook. So let's see. A little bit about how the data is different, because we've changed the scenario, and so now the way we think about the data is slightly different. So in the last part, there was this 59,000 row data set that had all of the data in it, and we were just using all of the data for training or 80% of it for training, 20% of it for testing. But now what I've done is I've split up the data into 6 almost equally sized subsets that have about 10,000 rows apiece. And if you got one of the data sets from the thumb drive, you have this. If you just downloaded the data from Driven Data, there's a script in the Git repo. I forget exactly, datasetup.py, that will go in and split up the data for you. It just orders it by the date and then takes slices of 10,000 and stores them into 6 different data sets that are like dataset 1, dataset 2, dataset 3. So the scenario is that dataset 1 is, let's say, the first dataset that we have, but we should build something that then it can run on dataset 1 or dataset 1 plus dataset 2 or dataset 1 plus dataset 2 plus dataset 3, and so on, and like make some maybe meaningful comparisons between all those different ways that we might be building the model. Again, we're going to move through this a little bit faster than I originally planned, but solutions are in the Git repo. And then one more thing that I'll add is, sort of by design, only maybe 10 or 12 of the 16 steps have working code, because some of these we broke into pieces and you weren't able to, you kind of have to, you solve one piece in like a step, but then that just means that you hit another wall in the next step. So in general, most of this code should run, but there are a few places where the code doesn't actually run. So if you're seeing it not working for you, you might just be looking at one of those cases. So don't panic. Okay. So the first thing is, if none of you have written a script in Python before, this is actually just like a good general purpose way to get started with scripting in Python. It's a little bit of this if underscore underscore name equals equals underscore underscore main syntax. And we won't go too much into the details about why you do this, but this is just a good Python best practice for when you're writing a Python script. So this was the starting point for this, is just setting up your script in your text editor so that it has literally this format. And then as you can see from this code snippet, then it's just like reading in the CSV file and printing out the top of the CSV file to your terminal window. So this one, I will actually take a few minutes and let you work on getting this up and running on your machines, just so then you have the general setup. Again, this code doesn't do anything that interesting, but I want to make sure that as much as possible, you all have the ability to edit and run these files. So let me give you just a few minutes to get that running right now. Is everyone familiar with, well, here, let me show you how to actually run this just real quick, for those of you who haven't worked with Python scripts before. But if you write, so I'm now in the step 1 solutions directory. My code just looks like this. So that was just the code that I had on the slide there. And so the way that I run this is I type python model.py, and you just hit enter. And then that's going to run the script. So this is obviously just printing out the top of the data frame. But for those of you who are newer to scripting in Python, let me leave kind of these windows up side by side so you have that for your reference. And I'll give you a few minutes to get that up and running on your setup. So if any of you are having a little bit of trouble with the directory path, again, my apologies for this. I think the place that it might be going to look, or where the data is actually stored for you, is in a thing called capital D data, if you got the data sets from those thumb drives. So if you're having trouble with getting, it says it can't find the files, but you got your data from the thumb drive, that's probably why. So apologies for that. But let's keep going. Okay, so the general thing that we're going to follow here, and that I think is good practice for structuring programs in Python, is that you'll have this main function, and what that main function does, you try to keep it as light as possible. So when there's big pieces of code or logic, or there's an algorithm, that should happen somewhere else in a different function that's in the same script. But we try to keep main very, very light. It's just like a controller that sends things out in other directions. So the first example of that, and I won't ask you to code this up, but let me just show you the example, is the first thing that maybe you want to do is to have some machinery for handling the data files. And I'll say what I mean by this in just a minute, like what I have in mind for this. But the first thing I want to do is point out this is now the solution for step 2, or like kind of pseudocode for the solution for step 2. And you'll notice that in main, now we're not building out very much more additional code in main. There's all the data handling that we want to do, we're sticking in its own function called, in this case, handle data files, that's going to do some stuff and then return back to us data frames that then we'll turn around and like do some stuff with. But the idea is to try to keep main from becoming really, really heavy. We want to make our code, this is what we mean by saying the code is modularized, is that it's broken up into pieces that hopefully each piece is solving like a concrete, discrete step of the problem. So what are we doing with the data handling? So one of the things that I spent a lot of time thinking about when I was putting this together is we want to have very reproducible and predictable behavior from our machine learning algorithms. And in particular, when we're always going to be training and testing our algorithms like we did in the notebooks. But now it's really important that we keep track of which events go into the training set and which ones go in the testing set. Because one of the things that we're going to do later is we're going to have multiple different versions of models. And for each training or each testing example, we're going to want to say, did model A get this question right? Okay, what about model B? And like, what does that tell us about where model A and model B are strong relative to each other? So we want to be pretty conscious of making sure that the same cases are being used as training and testing data in each of the different versions of the models that we might want to do. And so I spent a lot of time thinking about, okay, is there a way that we can make the train test split very reproducible? Like we're going to set all our random seeds, and we're going to be very conscious of, maybe we want to have it in just the same place for every data set, or maybe maybe we want to, I don't know. I really thought myself in circles and then was explaining this to a colleague and they were like, oh, well, why don't you just, the first time you read in the data set, just say, on this data set, this is my training data and this is my testing data. And just write those data sets out and never change them, which is a much cleaner solution. Because then like, you don't have to recreate them each time, they just exist. You do the work the first time, and then you write the data sets and you don't touch them again. So in the future, if you want to use those data sets, that's fine. You're certainly welcome to. But it should go and like retrieve the data sets that you've the data sets that you've already made instead of recreating them. So I don't know if that was like the clearest explanation. It might become clearer later on, like why this is so important as we're trying to do comparisons between the two models. But what I did in step 2, let me just show it to you real quickly, is now there's this file up here called handle data files. You'll notice that it has a doc string to it now. This is another piece of scikit-learn best practice, is you try to write out at the beginning of the function what the function does and what you should expect from it. And so now this function is where I do things like create a train test split on my data set. And then my training data set, I just write to a data frame. My testing data set, I just write to a data frame. The names of these files is tied back to the name of the original data set that I sent in. So if I send in data set 1, it's going to create train 1 and test 1. If I send in data set 2, it's going to create train 2, test 2. And so this is the way that I keep track of whether I have already created a training and testing data set for any given slice, in which case I just go retrieve it. But if I go in and I say like, okay, I'm interested in building a model on data set 4, it goes in and looks for train 4 and test 4, and if it doesn't see them, then it knows to create them, and if it does see them, it just retrieves them. So that's actually what I do in step 3, as I recall, is add in that logic so that it knows, it adds in the logic so it goes and looks for the data sets before it tries to create them. So that's what this path bit does right here. I know that I'm algorithmically generating the names of these training and testing data sets. So I know what they'll be called when I create them. And so I say, go and look for files that already exist, that have those names. And if they do exist, that's what this if statement is. If they do exist, then just pull out those data sets and return them to me. If they don't exist, then create the train test split and then write out the data sets for me to retrieve next time. So that then I'm not continuously having to like reinvent the wheel on the fly and like always wondering if I'm reinventing it the same way every time. Do you have a question?
So every time you're running the model, you're replicating running and splitting the state?
So the question is, every time I run the model, I'm replicating and splitting the data? No, because it's just overwriting the, if I were to go to step 2, it would be overwriting these files over and over again. So it's not creating new files, but it is overwriting them. When I add in this stuff in step 3, I go and check first before I create the files. Then I only create them the first time, and then I never have to create them again. Yeah, so you want to, a lot of machine learning, in my opinion, is bookkeeping around your data sets and making sure they have good names and you're putting them in places where you can find them and that kind of thing. This is a step in that direction. If you are sloppy with your data sets in machine learning, it's going to be really tough on you. Another question, yeah?
Continue that.
Yeah.
But you are replicating the data set when you're splitting.
I am replicating the data set when I'm splitting it. That's right. So I sent in a thing called data set 1, and then I made 2 things called train 1 and test 1, and those all have the same events in them. They're just partitioned in different ways. That's right. So we're paying a small price in, storage footprint for hopefully clarity later on. Okay, so that's what step 3 is if we see that the training and testing data already exists, go recognize it and go and retrieve that. And then step 4, this is just good Python life lessons, is using logging. So if you're anything like me, when you're building out a machine learning workflow, any kind of code really, you use print statements as your main currency for debugging. So you put a lot of print statements in there that are printing out intermediate states of your like algorithm or your workflow. And the thing about print statements is that then once you've, well, let me tell you how this usually goes for me, is that I put in a bunch of print statements when I'm debugging, say, a part of my code. I find the problem with a part of my code, and now I have this really like loud, verbose code every time I run it. It's printing all kinds of stuff, and so I want to clean that up. I want to turn it off. So I go in and I delete all the print statements, or maybe I comment them out, but then like my code starts to just be full of comments, and that's not really ideal. So I delete all my print statements, and then like 2 weeks later, my code breaks again, and I have to put all my print statements back in. And it's just kind of this not really ideal cycle. So a logger is a really nice solution to this problem. A logger is kind of like a smart print statement. And the thing about loggers is that you can set a level to how verbose you want the logging to be. So logging.info is kind of a middle level. You can say, logger, only tell me something if there's like a warning or an error or something really like alarming is happening. Logger.info is something like, it's kind of up to your discretion how many statements you want to put as info level, but usually I'll put like inside each important step of my algorithm, I'll put like an info message. Hey, here's the step that you're in right now. Here's some important things that I'm doing. And then there's stuff like logger.debug. And this is one of the more verbose, the most verbose settings. So you can have potentially a lot of debug output that you might want to have. So I've set logging to this middle level. And then when I'm actually in my code, instead of having a print statement, I would have a line kind of like this one, like logger.info. What I've said is like, okay, go in and find a data set. And regardless of if you find a data set, tell me what's going on. So if you find it, print out a message at the info level that says, I found the data set and I'm retrieving it. If you have to create it, tell me that you didn't find it and you're creating it. And if I wanted, for example, put these at the debug level, then I would have to then in general, they wouldn't show up at, if I'm looking for the info level of logging. I don't know if I'm doing a great job of explaining this, but basically the idea is when you're building out software, you might want to have different levels of verbosity that you want to flip on and off. And logging is a much better way to do that than print statements. So when you're developing this stuff and when you're handing out to someone else to use, logging is a really nice way to do that in Python. Again, that's bigger than machine learning or data science. That's just a fairly nice best practice. So at this point, I wanted to stop and take a little bit of evaluation of how the first part of our talk is comparing to the second part of our talk. So in the first part of our talk, what was the bare bones code that it took for us to read in the data sets, set up a training testing split, and yeah, that's basically it. Of course, I don't expect you to actually read this code, but it's just for visual impact. The easy way is, I think, 4 lines. The right way, the thing that's going to be allowing you to do this very reproducibly, very reliably, with nice logging, all this sort of stuff, that was 3 columns. So this stuff is fairly expensive to do. It's really easy to get flippant and think that once you've sprinted through and solved the first pass of a problem, you're 90% of the way there, and you just need to clean it up a little bit. In my experience, the better way to think about data science software and machine learning software is that the algorithm is like a payload that sits on top of a rocket. We built the payload in the first part of this talk. We are now building the rocket, and it's much, much bigger than the payload is. And so it's just, this isn't to scare you necessarily or to discourage you from writing good code, because I think it's really important, but just to stress sort of how it's a totally different ballgame, but it's really, really important in my experience. So let's keep going. So the first part of our talk, what was the bare bones code that it took for us to read in the data sets, set up a training testing split, and yeah, that's basically it. The So one of the things that I said at the beginning is that we want to keep our main function as light as possible. We want to have, like, what are the big pieces of the workflow that we're going to build? And let's start to architect out the program in a way that supports that. And so I think it's not a bad way to develop software to say, what are the pieces going to be called and what are the things that they take in and they give back? And just write like those function definitions and like the doc strings, and then go in later and fill them in. And so we're kind of gesturing towards that with this part of the talk. So what are the things that we're going to want to do with this for sure? So number one, we've taken care of getting the data in. So that's solved. Once we get the data in, the next thing we're going to want to do is build a model on our training data. So we'll make a function that's called build model. And then we'll maybe have another function that's going to take the trained model back from after it's been built. And using that and the testing data is going to make a set of predictions. So there's like little subclasses within there that would maybe, we could unpack this further, but those are sort of the big moving pieces that I can see right now. So what I did was try to just write out the names of the functions and what they will take as inputs and what they'll give as outputs. So for me, that was build model and then run predictions. And then your main function, again, is still staying pretty lean. You're not doing real serious computation in main. You're doing it elsewhere in these like dedicated functions. Let me pause for a moment. Are there any questions about some of the stuff we're covering right now? I know this is going super, super fast. Yeah? What about overfitting? Yeah, so overfitting, the main protection that we will have against overfitting is making sure that we're diligent about our training and our testing data. The testing data will let you know if you're overfitting because you'll see that the accuracy on your testing data is really poor. This is not particularly optimized for protecting you against overfitting, though. It's really saying, like, you already know what kind of model it is you want to build. You have confidence from the first part of the talk that it's not overfitting, and now we're building it in a more robust way.
I'll try to rephrase it.
Sure.
That, you're not talking currently on overfitting, but said previously that you're not touching the training set and the testing set. Let's say that you found that you know the module is overfitting.
Yeah.
That then you would touch it.
So the question is, if we're not not touching our training and our testing data, if we're like nailing down our training and our testing data, then if we end up overfitting, would we maybe have to go back and revisit our training testing split in response to that? Is that the question? Okay. So in general, if you find that you're overfitting, the solution to that is not to go change around which data points fall into training versus testing. It's to go back to the hyperparameters of your model and try different hyperparameters. So in general, once you set the training and testing split, you shouldn't have to change it. Even if you're overfitting, the way that you would address that is by changing the model, not by changing the data allocation. Yeah. Any other questions? Okay, cool. So, this isn't going to work, but like, sure, why not? Let's try it. So I'm all in favor of trying to get an answer as quickly as possible. So let's try to get an answer as quickly as possible. So I know from my notebook that, okay, I have my data being read in, so that's good. I have some idea of the model that I might want to build. So by that I mean this model pipeline with like a select k-best and a random forest. Like that seemed to be giving me pretty good results last time. And so what if I just take my testing or my training data and just stick it into my model pipeline and say, like, can you just try to fit this? It's going to fail, and it's going to fail for two reasons. Number one is that my labels are strings, remember. This was that functional needs repair, non-functional. We have to map those back onto integers. We have to do that again. And we have to do something similar with coming up with integer, or in this case, dummy encodings for the features. So in this case, I remembered to integer encode my labels. Let's see, so we're on step 6. So in step 6, I've written a function called encode labels that's going to turn my functional, non-functional, and functional needs repair into integers, the same way we did in the notebook. But I haven't actually bit the bullet on the features yet. And so what happens in this case? Well, it's pretty predictable. It's going to crash. How's it going to crash? It's going to throw some kind of error that says it doesn't know, it can't cast hand pump to float. So some of you actually saw this in your notebooks. This is just the same thing again. It has a NumPy array that it expects to see full of numbers, and it gets a thing called hand pump, and it says that's not a number, which is a fair point. It's not a number. There's one more thing I want to point out to you here. Another little piece of scikit-learn fun, I guess, which is that scikit-learn has this thing called label encoder that's actually designed for taking string labels and transforming them into integers. So I'm just using that here instead of writing a function that does the mapping by hand. And we'll make use of this on the features as well in a little bit. We're going to kind of hack it. But that's all that label encoder does, is it just takes the strings and it turns them into integers. So I have my labels covered at this point, but I have to go back to the features and get that all sorted out. So let's think about the features a little bit. What am I going to have to do here? So it wasn't just about dummying the features. It was like I had to come up with a few different fates for each of the columns in my data set. Some of them I have to dummy. Some of them I want to leave alone. And some of them I want to drop. And so let's think about ways that we can kind of accommodate each of those different use cases. So the first thing is I have to keep track of which column gets which treatment. And in a perfect world, actually a good way to do this is to have some kind of configuration file that drives the whole modeling pipeline. And in that configuration file, you can say which column goes into which, gets which fate. I didn't have sort of like the time in this talk to go full-blown configuration file. But what I have done instead is I've created a couple of special functions in my workflow where I define what are the columns that get dropped and what are the columns that get dummied. And so the point here is that I'm going to have a set of code that actually goes through the logic of manipulating the data. And I want to break apart from that the part where I say what data gets manipulated, because I want to have some flexibility there. I don't want to have, as much as possible, I want to have the algorithm kind of like have this semi-permeable membrane with the settings of how I'm running the algorithm. So breaking out some of these specific features to what are the features we're going to drop, what are the features we're going to dummy, breaking that information out into its own function is trying to set up a little bit of a boundary between my algorithm code and my data-specific code. And so what I've done here now is there's a couple of functions as I'm here. Let me just go to the code and be a little more concrete about it. OK, so now there's a couple of functions that are at the top of my script where I'm just defining a list of all the columns that I want to dummy and defining a list of all the columns that I want to drop. And then there's going to be another place in the code where I actually go through and do the dummying and do the dropping. But it's going to be a lot easier for me to like find and change these columns if they're in their own special place. So that's why I put them there. And then I have this function that I built out a little bit earlier called build model. This is where I'm doing all the stuff that I have to do to build a model that's not handling the data files or running predictions. So now I'm doing stuff like, hey, what are all the columns that I have to drop? And then let me go ahead and drop them. And now I'm starting to move toward a single function that's doing all of the data pre-processing. And then eventually you can see, I hadn't pointed this out yet, but it's good to notice that we have kind of this data pre-processing block up here that's going from our raw data frame to something we can stick in a machine learning algorithm. And then down here we actually have the pipeline that we're building and fitting. So again, this is like the payload. This is the algorithm right here, but we're building out all of this infrastructure to like get things set up for sending it into the algorithm. So step 8 is where I actually dummy. And this was super fun and this was a lot harder than I thought it would be, to be totally honest. And I'll show you why. Let me pull up. Okay, so how are we going to dummy our data? So one of the things, the easiest way to do this is with pandas.getDummies. And a lot of you, I think, used that in the notebook when we were going through the first time. The thing that's hard about pandas.getDummies is that it doesn't have a way of remembering what was the dummying scheme from one data set and then applying it to a different data set. And that's a problem for us because we want to come up with a dummying scheme on our training data and then apply it to our testing data. So we need to have that like information transfer from how did we manipulate the training data and then like manipulate the testing data in the same way. So what do I mean by that? So if this is an example of our training data, then our training data has 3 cities in it, right? It has Chicago, it has San Francisco, and it has New York. And when I dummy it, what this is implicitly doing is it's saying like, oh, if you see Chicago, that's the first column. If you see San Francisco, that's the second column. If you see New York, that's the third column. That's what I mean by the scheme that it's using to dummy. And the problem is that what if in my testing data set, there's a column or there's a value that shows up that I didn't see in my training data? How do I know which column it's supposed to go to or what to do with that? Likewise, let's suppose that my testing data only has Chicago and San Francisco and it doesn't have New York. Then my testing data set is going to have 2 columns. My training data has 3 columns, and like the model isn't going to work because it's expecting a different dimensionality of data than what I'm sending in. So that's what I mean by I have to keep some memory of the dummying scheme that I got on the training data and transfer it to the testing data. This turns out to be a huge headache, and again, much harder than I thought it was going to be. Just as like an editorial aside, dummying seems like it's the easiest thing in the world, and it's actually really, really hard. Or it's really hard to like get generally and get correct. But that having been said, I kind of sat and pounded my head against it for longer than I would care to admit. And here's the solution that I came up with. So pandas.getDummies doesn't have memory of the last time you dummied with it, but scikit-learn transformers do. So scikit-learn transformers, they have fit and fit transform, and then they just have dot transform. And so if you call fit on dataset A and transform on dataset B, then it can do that, it'll apply the same scheme to both of the data sets, if that makes sense. So I leaned on scikit-learn pretty heavily here. Even though pandas has a nice tool, scikit-learn has something that's closer to what I want. And so there's 2 steps that I have to put in here to do the dummying. So the first is that I had to, remember, I had to turn all of my, this is a little bit funny. So the scikit-learn dummying function, remember it's called one-hot encoder. As it turns out, one-hot encoder only works if the values in the column are integers, which is just like a funny thing. There's no particular reason why you would think it couldn't work with strings, but it doesn't work with strings. It has to take integers. We don't have integers. We have strings, right? We have things like hand pump and gravity and riverside and whatever all these values are. So we have to do this kind of painful 2-step transformation. We have to turn our strings into integers. We have to turn our integers into dummies. Is this interesting? Not particularly. Like, I was a little bit crying inside when I spent a lot of time trying to figure out the best way to do this. I say this to you not to, again, to scare you away from this, but just to point out that even for some of the simplest tasks, trying to figure out like the exact way to get the pieces to fit together. Scikit-learn has a lot of really lovely pieces, but sometimes getting them to fit together is a little bit harder than you would guess. And there's sometimes a little bit more. This is something that it's really easy to skip over in, say, like the homework for a course or in a Kaggle competition or something. But in real life, you kind of have to stare this stuff in the face sometimes. So hopefully, like, you will have like long and fruitful careers in, or hobbies in machine learning and data science. And at some point, you will probably hit something like this. So hopefully, the next time you hit it, it's like a little bit less painful than it was for me because you have some of this code. But anyway, so you have to think pretty carefully about what it is you're doing when you're training a model, what it is you're doing when you're fitting a model. And in the case of dummying, that's actually pretty non-trivial. So at the end of all that, though, the great satisfaction that I can take, once I've got that dummying sorted out, though, everything's pretty easy from that point forward. So I can send the data into my model pipeline, and it fits, and everything's great. And so let me just run this for you right now. This is step 8, and see if this, make sure this actually works. Yeah, so I've given myself a bunch of debug output here. So I have a pretty verbose, some pretty verbose output about what are all the different columns that I'm dummying and what are the different classes I have to account for and that kind of thing. But then at the end, it actually does work. So eventually it gets there. Yeah, question?
So you said it was good that we had the logic left from the training data to give the test data. That doesn't answer the question. What if the test data has values that need to be dummied that we're not?
Yes, excellent question.
Given other.
Yes, we are getting there in like step 11. Yeah, no. This is exactly the stuff that you should be thinking about. So the question for those in the back is, we didn't actually answer the question of what if there's a value that shows up in the test set for the first time? What should we do about that? And it has a pretty intuitive answer, which is maybe now that we have a little bit of, we have some foresight, maybe we shouldn't have n columns. We should have n plus 1, where 1 is none of the above. And we just have to be smart when we're making up our training scheme and like make that adaptation to it. Again, technically, this is a little bit of a hassle, but I'll show you how to do it. It's not really that bad. But yeah, it's a really good question. So I'll skip over step 9 a little bit just to say that, well, here, let me point out one thing about step 8, which is that now my build model function is getting a little bit bloated. So the bulk of build model at this point is not actually building a model. It's doing some feature pre-processing stuff. And so this is a good place in which you kind of take a deep breath and you break out your feature pre-processing into its own function. So that, again, we're trying to keep each part as kind of single purpose as much as possible. So that's what step 9 is about, is let's take some of that feature pre-processing code and give it its own function called feature pre-processing. So now feature pre-processing is a totally different function that's got all the same code in it that it had before. So this is dropping columns, this is dummying columns, and this is relabeling columns also, so that after I've done the dummying, I can still keep track of what columns actually mean. This is all now just happening in its own dedicated function. So I'm keeping build model comparatively clean. This is what build model looks like now. This is the text for build model. It's 15 lines or so. It's a lot cleaner. So, done a little bit of cleanup. Okay, so that's pretty cool. Now it's time to try to make predictions with this thing. So let me, actually, I'm finding it more successful to just lecture from the code than from the slides. So let me pull up. Okay. So now I'm all the way down in my main function. This is like the lightest of wrapper functions. And so what is it doing? Well, this is, yeah, we'll go into what this is doing. So build model is now building the model. So this includes the feature preprocessing, and this includes building and training the scikit-learn model pipeline. And once I'm done with that, I want to get two things back. I want to get the trained model, because this model I'm going to be then sending my testing predictions into it in order to actually make the predictions. And then the second thing, and this might not have been obvious at the outset, I also have to bring back the label encoder and the one hot encoder that I used to dummy my training data. So there were a bunch of like dummying schemas that all of those transformers had to like figure out and deploy on our training data. And I want to now take those same transformers and apply the same transformation to my testing data that I did to my training data. So I'm being totally above board about my testing data. I'm treating it like it's data that I've truly never seen before. It was in no way taken into account when I was doing any of the manipulations on my testing data set. This is going to be a true representation of what a totally unseen data point, the path that it would take through this machine learning model. But I need to remember what the dummying scheme was so that I can have data in the same format from my testing set that I had from my training set. So
you're relabeling the whole data set?
So I'm dummying not the entire data set, but like 75% of it, yeah. So I've dummied out the whole data set, and I have to remember how I dummied it so I can dummy the testing set the same way. That's what I'm doing here. Shoot, now I have to keep track of all these like label encoders and one hot encoders. And again, there's no nice solution here, not really. It's just like a bunch of stuff that you have to keep track of and then return back from the process of building the model. So that's what TT is. This is my shorthand for trained transformers. And this is a big dictionary. This got 39 different, or 30 or so different label encoders, 30 different one hot encoders. And I'm going to use those to transform my future data. Again, 90% of the battle with machine learning is good bookkeeping. So I'm going to take my model, I'm going to take the trained transformers, and I'm going to take the test data frame, and I'm going to send that into a prediction function. And I'm going to try to do something to send my testing data set through the same transformation process that I put on my training data set. And in particular, well, this is what we're talking about right now. This is a big hassle. In particular, the thing that I will run into as a problem is the thing that we were just talking about. So there's going to be values that show up for the first time in my testing data, and what am I going to do about that? One hot encoder is like sort of okay with this, but label encoder is the thing that I'm using to turn strings into integers. If it sees a new string, it will break. So any thoughts about how we're going to deal with this? We a little bit talked about it before. Yeah, have an all but, exactly. So I have to, number one, backtrack a little bit to the dummying that I set up in the first place and say, don't just dummy what you see, dummy with an extra slot at the end for what you didn't see, that I'm calling like other. And then the second thing is that I have to now introduce some logic so that when I see something that's new, it recognizes like, oh, this is just a new thing. Don't throw an error on this, just put it in that extra column. So this is a little bit of keeping track of which columns are new and reassigning their values to other. Again, not the most exciting thing in the world, but you need to do it to make it work. So at the end of that, once you've sort of gone back and retraced yet again how you're going to do the dummying logic, then I promise it does actually work. So let me show you a working version of the model a working version of the pipeline. I think this one works. Okay, cool. So what this is doing is it does all the dummying garbage on the training data, fits the model pipeline, again, that's not that hard, reproduces the entire thing on the testing data set, and then at the end, the last line that I have here, is me actually making a set of predictions on my test data. So this is actually it working end to end now. I've got my model training, I've got it making predictions. That was really painful and not super fun, but I'm being very disciplined about how this works. So this is gonna generalize really nicely. And so the next thing that I would want to do, we'll start to slow down a little bit now because this stuff starts to get really interesting. So let's evaluate the models. I think this one works. Yeah. Okay. So this is exactly the same workflow as before, but now I've added a classification report at the end. I'm going to let you look at this for a second, and then as you notice things, raise your hand. What are some of the things that you notice about this model? Where are the places where it's weakest in particular? One is terrible. Yes. So what's going on with 1? Any ideas why 1 is so bad? Because we only have 65 data points. So in general, the more data you have to train, the better it'll do. This is an imbalanced class problem. And moreover, we just don't have a lot of data here. So that's not great. And so the question that you might be rightfully asking yourself is well, what should I do about this? And if I were a machine learning, the machine learning researcher, my answer would be go collect more data. I assume that you're going to get the same type of data that you had before, so it's still going to be imbalanced, but just go get more of it. And maybe that will fix the problem, I hope. That's a good first guess. There's other things that I can do if it doesn't fix the problem, but my favorite thing is to tell somebody else to go work harder and then just stick it into my system rather than me trying to work harder, right? So this is what I do in step 13. And let me show you just quickly what it is I'm doing, so that that's all crystal clear. So now this is my main function. It's a little bit bloated, but maybe not too bad. And now I'm doing, this was what I had before. So this was dataset1.csv. And now I have a second thing that's got dataset2.csv. And I've made an update to handle data files. Now I can send in a list of 2, in this case 2, but 3, 4 if I want files. I can just send in a singleton file still, and it'll do all of its stuff. But because I was pretty careful about the way I constructed it, I can now send in as many data sets as I want, and it's all going to process them intelligently and do what I think it should do in terms of going and retrieving the data sets properly if it's seen them before, or creating them if it hasn't seen them before. And so what I'm doing when I send in 2 data sets now is I'm effectively doubling the size of the training set. And so my hope is that now with the extra data, class 1 is going to do better. And there's really no way to know for sure if it will or not before you run it, so we'll just run it. And then you can take a look. So hopefully this is, so there's my first model. And then there's going to be a bunch of printing. So kind of look and memorize some of the numbers that you're going to look at for the next one. Here's the next one. Let me see if I think there's a screenshot where I made these the same size. Let me throw this up.
This is random forest?
Mm-hmm. This is random forest. So hopefully you can see them. This is, I think the bottom one is actually running over 3 data sets now instead of 2. So there are a lot of things that we could say about this, but just first glance, is my hypothesis correct? I just needed more data. Yeah, it helped. It helped a lot. I now have something 5 times as much of class 1. I'm really just looking at class 1 right now. Like class 0 and class 2 probably get a little bit better.
0 actually goes down.
The 0 goes slightly down, so we might have gotten a little bit unlucky there, or maybe something else is going on. I don't exactly know. So that's probably like something to check out. But what I now have is some evidence that if I add in more data, it's going to get better. But I don't know for sure. So one of the things that could be happening is I could be just adding in more data, and the whole model gets better. And sort of that's why I'm winning in the second case. But the other thing that could be going on is that there's 65 examples in the first one. There's 310 examples in the second model that are totally new. And so I wonder if what's happening, alternatively, maybe data set 2 and data set 3, those examples are just really easy for me to classify correctly. So maybe what hasn't happened is that the model has gotten better. Maybe just the underlying data set has changed, and I'm just better at predicting certain types of class 1 events, class 1 events, and I happen to see more of them in this data set. So I don't know which of those two worlds I live in. I don't know whether this has to do with the data or it has to do with the underlying model. So I'm actually not going to explain right off the bat how to solve this. We'll go to it in a second, but first I want to hear thoughts from the audience about how you can disambiguate better model because more data from just different data.
I don't know how to statistically do it, but my first investigation would be how much different is the model, right? If the model's a lot different, then it's making better predictions. But if it's the same model, then it would be you just have data that fits the model rather than the model fitting the data.
Yeah, so for those in the back, the response was, well, how different are the models? Do we have basically the same model here, and it's just like it's still missing all the things it was missing before, but like but the data's changed. Yeah.
As opposed to the model's fitting the data.
Yeah, and so so you're on the right track. I think that's the right idea. The thing that's hard is to articulate what makes a model different. So this is a random forest, right? It's not very interpretable. It's hard to look at something like feature importance and say, is this a different model? So what other methods besides something like feature importance? Or like how would we define what makes two models different? Yeah?
How well it can predict the rest of the data?
How well it can predict the rest of the data, and in particular, we have 65 examples in common between these two testing data sets. Remember, we were very careful about always using the same testing data for each slice, and the data that we used for the first model is just a subset of the data that we used for the second model. So we have two models that have made predictions over the same examples. And so what that means, one of the ways that you can define what makes a model different is, does it make different predictions on the same case? Like, it seems like really obvious, but this is something that you miss a lot of the time if you're doing something like looking at accuracy or precision or recall. Those are big aggregated statistics, and they just say, on the whole, how many is it missing? How many is it getting correct? If you go through row by row, and you say, which ones is it missing? Which ones is it getting correct? Are they always agreeing on the predictions, or are they making different predictions in different places? That's a really good heuristic for like, are these models doing effectively different things? There's still more ways that you could unpack what makes a model different or the same, but a really good rule of thumb is like, models that are the same make the same predictions. So if you check what the predictions are, and the predictions are the same, then like the underlying model is pretty similar too. So what are we going to do about this? What I would suggest we do, and what I did, and I'll show you what happens, is we take those 65 examples that we have both models predicting, and we see how many times does model 1 get it wrong and model 2 get it right. So this is really unpacking for us. If we see that like model 1 gets a bunch of them wrong and model 2 gets them wrong too, then that just tells us that, that the underlying data has changed. But if there are a bunch of cases that model 1 gets it wrong and model 2 gets it right, that means model 2 has sort of learned better representations from having more data. Does this make sense? OK, cool. So let me show you what actually happens. So this is step 14. So what I did was I went in and I added a step that steps through those predictions side by side. And I said, give me all of the predictions, the name of the index of the row for all of the predictions where model 1 gets it wrong and model 2 gets it right. And then what I'm going to look for is for how many of those print statements do I get, basically. So let me show you what this does. So it's rebuilding model 1. Now it's rebuilding model 2. And look at that. There's a whole bunch of, there's, you know, whatever, probably 50 different lines here. So this is saying that there's a lot of examples where we've kind of like learned some pattern that allows us to go back and like get these questions correct in retrospect. So this is pointing towards the model has actually gotten better from having more data in it. It's not just that the data is different. It's the model itself is better able to pick up the patterns because of this trend that we see.
Wouldn't you want to check the other way around too? The ones that got it right, but then now model 2 get it wrong?
That's a really good point. Yeah, and this was a place where I got a little bit lazy, but it's an excellent point. So the question was, don't you want to check it the other way too? Places where model 1 got it right and model 2 got it wrong. And yes, you do, because in general, I'm just saying where are all the places where model 2 is winning, but model 1 might also be winning in some other places too. So in order to say that we like really have a grasp on this, we would want to see that there's many more places that model 2 is winning than there are places that model 1 is winning. That's a really good point. Yeah. Questions about this stuff? This is one of the things that I think is very often disregarded about model comparisons. There's a lot of places that will like compare models based on things like accuracy, precision, recall, AUC, if you're familiar with that one. They have these aggregated metrics. But in order to really understand if two models are comparable, you really have to go row by row and say where are they the same and where are they different. And that's something that's almost never done. So, but I think it's really important. Yeah?
So are you saying that you're keeping the same test set for both your training data sets?
Yes. So I have a test set that, so the second model that I build is using like 20% of the, or I guess 33% of the data that I have for my second model was in my first model. So then I have test examples that I have for my first model and for my second one. So it's the exact same events that I'm looking at for both models. And those are the events that I'm comparing. Yeah. And I can only do that because I was really, really strict with myself at the beginning about making sure that I have the exact same test set every single time I run over a data set. We went through sort of all that hassle of writing out the files and like going and retrieving them and not making that up on the fly. And it was so we could do stuff like this later on. Okay, almost there, 15 more minutes. So there's just two more cute little things that I wanted to show to you, and then the rest of it can be questions. This is, again, a little bit more Python than machine learning. So the first is sticking a command line interface on it. So for someone who wanted to run this, let's say the analyst who's running this in the field, if they wanted to go in and change the file that it's running over, they would have to go in and actually edit the script itself. They would have to change around the name of the data set. So what I've done in, what is this, step 15, is I've added a command line interface, so I can just, when I run the program, I can just pass in the name of the data set when I do that. So let me show you what this looks like. So I'm using what's called argparse in Python, and it's now going to take this optional files parameter at the command line, and that's how I'm going to tell it which files to send in. So when I run it now, it's Python, oops, and then it says files, and then I put in the name of the file that I want. So this one, I'll run it on dataset1.csv, and then I've set it up so that I can put in as many files as I want. So I might say dataset2.csv, and somebody yell out a number between 1 and 6, between 3 and 6. 5? Okay, I actually haven't run it on 5 before, so if I've done my job correctly, this will run smoothly. So what this is going to do is it's going to build 2 models, one of them just on dataset 1. So that's our dataset 1. And then the second one is going to be on 1, 2, and 5. So it's going to be 3 times as big. And yeah, so there's my new model. There's my second model. Again, because my data set is bigger, I've got some, I'm doing better with class 1, which was my weak spot before, and then I have my same output as before of where they're making the same predictions. And then the last thing that I wanted to show you, and then we'll break for questions, is testing. So quick show of hands, how many of you have ever written a software test before? So a few, but not by no means a majority. So testing is just a really good thing in general to do for software. It makes it so your code is less likely to be buggy when there are changes because of stuff that you've changed, because of external libraries that have changed, whatever. It makes it a lot more robust and just gives you overall confidence that your code is doing what you think it should do. Testing in machine learning is definitely a good practice, but it's really hard to do, I think, compared to regular software testing, because with regular software testing, it's kind of just you and the algorithm for the most part. With machine learning, it's you and the algorithm and the data set. And so the answer that you get back for any operation is going to be very much tied up in the data set that you sent in the first place. So it's a little bit challenging sometimes to write like unit tests for machine learning code, but I've written one here to show you what this looks like. So I'm using PyTest. So now there's a script in here called test model. And I actually was messing around with this last night, so I'm going to go in and fix the test because it's broken right now. So what I'm testing in this code, there's 2 tests that I have here. One of them is trivial, and one of them is not. The first one is trivial, that test, assert true. That's just like, that's not really testing anything. That's just making sure that like I have my test set up properly. The second one is actually testing some of my feature preprocessing code. So one of the things that I want feature preprocessing to do is I'm going to send in a data frame, and then it's going to go try to figure out what are the columns that I should drop from this data frame. It also does a bunch of dummying, but let's just talk about dropping. It's going to say, what are the columns that I have to drop from this data frame, and then it should drop the columns. And so the data frame that I get back from that process should be the one I sent in minus the column that I said to drop. And so that's what this test is testing. I'm making myself a fake data frame that has 3 columns in it, chocolate, vanilla, and strawberry. And I'm doing something that's it's a little bit of fancy footwork here, but it's pretty cool, which is this thing called mocking. So one of the things that's hard about testing features to what are the features that I want to drop is that there's actually a lot of features that I want to drop. The way that this code is written is columns to drop returns like a big data frame or a big list of features. And I don't really want to have to deal with a data frame that's that big to try to just test whether the dropping is working or not. Like what I need here is like a speedboat, and what I have is a aircraft carrier. So I'm like, okay, I don't want this big 15 column list of all the columns that I want to drop. I just want to send in I just want it to drop 1 column. And if it drops that 1 column, then that's victory for this test. And so I'm hijacking the part of the code that says what are the columns you want to drop. And instead of having it return like this big long list, I'm having it just have a return value of strawberry. That's what the mocking does. It's a way of hijacking other pieces of code that I'm testing feature preprocessing, but feature preprocessing calls other functions. I'm hijacking those other functions to just isolate the functionality in feature preprocessing. And so what happens is once I've done this, I can do a much lighter weight test of dropping columns. And what I say is that what I expect feature preprocessing to do as I've set this up is I'm going to send in chocolate, vanilla, and strawberry. I'm telling it drop strawberry. And then the thing that I get back should not have strawberry in it. And that's all the test does. It's just like, did I successfully drop a column? Pretty simple, but stuff that's like easy to have break. Because like notice we wrote a whole bunch of code about how to dummy and drop these columns, but we didn't actually check that the data frame that we were getting back had the columns dropped. We kind of took it on faith that it was all working. So now we're fixing that a little bit, and then here's how you run the tests, is you just click pi.test. And then this is what a passing test looks like. So it has two little dots here, because there's two tests. There's like the trivial test and then the real test. And so it's scanning through and said I did a couple of tests here, and they all pass. If it doesn't pass, if I do something like vanilla, in this case it's going to drop a column, but the column that it drops will be vanilla instead of strawberry. So strawberry is still going to be there when I get the data frame back. But I said I don't want strawberry there, so this test is going to fail now. And so by having automated tests of all of the functions that I've written to make sure that the thing that they're doing is what I want them to do, I have a lot more protection than when I go in and I have to modify the code. I want to make sure that it doesn't break in production. Building out a fuller set of test suites for my machine learning pipelines is definitely a good practice to be in, especially for some of these manipulations. So this is just it's a simple example, but it's not a trivial example. Like this is a real test that's actually testing some functionality that we hadn't tested here yet. So I wanted to just give a nod toward that for those of you who maybe are familiar with machine learning but have never written tests before, that thinking about how to test machine learning code is definitely one of the things that kind of makes for varsity data science code. And then at this point, I think we're pretty far outside of like beginner data science 101. So thank you for indulging me. But again, this is the stuff that I think is really important that you don't learn anywhere else. So wanted to the extent possible, make sure that you at least saw it once and knew that it was out there. And so with that, I have just a few minutes left for questions. Thank you again very much for coming and for being a great audience and for kind of fighting and struggling through